a universe fit for life. Settle into the quiet of this moment and let your awareness expand outwards, beyond the confines of the room, beyond the sky, into the vast, silent expanse of the cosmos. Tonight, we embark on a journey of cosmic contemplation. We will not be exploring the inner world of the mind, but the grand outer world of the universe itself, and a deep, persistent mystery that lies at its very foundation. The mystery is this: the more we learn about the universe, the more it appears to be exquisitely, improbably, and miraculously suited for our own existence. From the precise values of the fundamental forces to the chemical composition of the stars, the cosmos seems to possess a set of just right conditions, a delicate balance that allows for the emergence of complexity, galaxies, planets, and ultimately conscious, observing beings like us. We find ourselves living in a universe fit for life. But why? Is this astonishing coherence a mere cosmic coincidence, a lucky accident of immense improbability? Or does it point towards a deeper principle of order, a grand design, or a more profound truth about the relationship between consciousness and the cosmos? For the next 3 hours, we will explore these cosmic coincidences, the anthropic principles that attempt to explain them, and the search for universal order. This is a journey designed to evoke a sense of awe and wonder, to relax the mind by placing our small, everyday concerns against the vast backdrop of cosmic mystery, guiding you into a state of deep sleep. Our journey begins with a simple act of recognition. The fact that you are here now, a conscious being capable of contemplating the universe, is the end result of a 13.8 billion-year cosmic story of incredible delicacy. This story is governed by a set of fundamental laws and physical constants, numbers that seem to be imprinted on the fabric of reality itself. These are numbers like the strength of gravity, the speed of light, the mass of an electron, the force that binds atomic nuclei together. For a long time, we took these values for granted. They were simply the way the world is. But as physicists in the 20th century began to create models of other possible universes, they made a startling discovery. They found that if you were to slightly tweak the dials of these fundamental constants, the resulting universe would be catastrophically different and almost certainly lifeless. Imagine a control panel for the cosmos. If you were to turn the dial for the strong nuclear force down by just a few percent, atomic nuclei would not hold together. The only element in the universe would be hydrogen. There would be no complex chemistry, no stars as we know them, no planets, no life. If you were to turn the dial slightly up, stars would burn through their fuel so rapidly that there would be no time for life to evolve on any orbiting planets. Consider gravity. If it were slightly stronger, the universe would have expanded and then immediately recollapsed in on itself long before life could form. If it were slightly weaker, galaxies and stars would never have condensed from the primordial gas. The cosmos would be a thin, cold, uniform soup of particles. The window for a universe like ours, one that is stable for billions of years and rich with complex chemistry, is incredibly, breathtakingly narrow. This is the fine-tuning problem, which we will explore in detail, but its implication is the starting point for our entire inquiry tonight. We seem to be living in a Goldilocks universe, where the conditions are not too hot, not too cold, but just right for our existence. This observation can evoke a powerful sense of unease or wonder. It feels too convenient, too coincidental to be a mere accident. It seems to cry out for an explanation. Why this specific set of rules? Why this particular, life-permitting universe out of a seemingly infinite number of possible, but sterile, alternatives? This question has led to some of the most profound and speculative ideas in modern science and philosophy. It has pushed scientists to develop the anthropic principles, a set of ideas that try to account for this observer-friendly universe. It has led to the development of the multiverse hypothesis, the idea that our universe is just one of countless others, and we simply find ourselves in one of the rare ones where the conditions were right. It has been used by some as a modern, scientific argument for a designer or a creator, a form of grand design. And it has led others to search for a deeper, underlying physical theory, a theory of everything, that might show that these constants must have the values they do for reasons of pure mathematical consistency. Throughout our journey tonight, we will explore all of these paths. We will look at the nature of order and entropy, the unreasonable effectiveness of mathematics in describing our world, and the way complexity seems to emerge from simple rules. We will contemplate theories that suggest the Earth itself might function as a single, self-regulating organism, and paradoxes that arise from the contemplation of an infinite, random universe. We will touch upon the philosophical and theological implications of living in a cosmos that appears so finely balanced. The purpose of this exploration is not to provide a definitive answer to the ultimate why. Such an answer may be forever beyond our reach. Instead, the purpose is to cultivate a state of awe. Awe is the emotional response to encountering something vast, mysterious, and beyond our ordinary frames of reference. It is a feeling that has been shown to reduce stress, increase feelings of connection, and promote a sense of well-being. By contemplating these cosmic-scale questions, we engage this capacity for awe. We shift our perspective from the immediate and the personal to the vast and the universal. In doing so, our own anxieties and concerns can seem to shrink in relative importance, creating a space for profound peace and mental quiet. As you continue to relax deeply, let your mind's eye open to the scale of the cosmos. Feel yourself as a part of this vast, intricate, and exquisitely ordered universe. A universe where the laws of physics seem to have conspired to allow for the possibility of your own conscious experience. Acknowledge the profound mystery of this fact, that you are living in a universe fit for life. Let this thought not be a problem to be solved, but a wonder to be held, a source of quiet, profound gratitude for the sheer improbable fact of your own existence, resting peacefully, floating calmly in a cosmos that is either an incredible accident, a deliberate creation, or part of a tapestry far grander than we can imagine. The fine-tuning problem. Having introduced the general idea of a universe strangely hospitable to life, let us now delve deeper into the specific scientific details of this mystery. We explore the fine-tuning problem, a collection of observations from physics and cosmology that, taken together, suggest the fundamental constants and initial conditions of our universe are balanced on a razor's edge for the existence of complex, intelligent life. This is not a vague philosophical feeling. It is a conclusion that arises from the precise mathematical models that form the bedrock of modern science. The problem is not that life is fragile. The problem is that the very possibility of any kind of structural complexity, from stable atoms to long-lived stars, seems to depend on an astonishingly improbable and delicate balance of these fundamental numbers. The fine-tuning problem is a profound cosmic coincidence that serves as the primary evidence for any discussion of anthropic principles or grand designs. Contemplating this cosmic balancing act is a mindfuck that questions whether our existence is a fluke of unimaginable proportions or the result of a deeper, hidden principle of order. Let the sheer improbability of your own being guide you into a state of deep, contemplative relaxation as you fall asleep. Let us begin with the forces that govern the universe. There are four known fundamental forces: the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. The relative strengths of these forces are crucial. The strong nuclear force is what binds protons and neutrons together to form atomic nuclei. If it were just a few percent weaker, only hydrogen would be stable. Deuterium, the stepping stone to nuclear fusion in stars, would not form. Without fusion, stars would not shine, and no elements heavier than hydrogen would ever be created. The universe would be a cold, dark, and simple place. If the strong force were slightly stronger, on the other hand, protons would bind together so readily that all the hydrogen in the early universe would have been rapidly fused into heavier elements. There would be no hydrogen left to form the fuel for long-lived stars like our Sun, and no water, H2O, a crucial ingredient for life as we know it. The existence of a universe with both stable stars and the chemical diversity needed for life depends on the strength of this force being in an incredibly narrow, fine-tuned range. Now consider the force of electromagnetism relative to gravity. Electromagnetism is vastly stronger than gravity, about 10 to the power of 36 times stronger. This immense difference is itself crucial. If gravity were slightly stronger relative to electromagnetism, stars would be much smaller, denser, and would burn out in a few million years, far too quickly for complex life to evolve on any orbiting planets. If gravity were slightly weaker, stars and galaxies would never have been able to condense from the primordial clouds of gas. The delicate balance allows for the formation of long-lived, stable stars like our Sun, capable of warming planets for the billions of years needed for evolution to work its magic. The properties of elementary particles also appear to be finely tuned. The mass of the neutron is slightly greater than the mass of the proton. This tiny difference is critical. Because of it, a free neutron will decay into a proton, an electron, and an antineutrino in about 10 minutes. If the neutron were slightly less massive than the proton, then the proton would be the unstable particle, decaying into a neutron, a positron, and a neutrino. In such a universe, stable atoms as we know them could not exist, as their protons would decay. The very stability of matter depends on this precise, delicate mass difference. The initial conditions of the universe at the Big Bang present some of the most stunning examples of fine-tuning. One is the flatness problem. According to general relativity, the geometry of spacetime can be curved. Our universe appears to be, on the largest scales, geometrically flat, or very close to it. For this to be the case today, the density of the universe at 1 second after the Big Bang had to be fine-tuned to an accuracy of about 1 part in 10 to the power of 15. If the density had been slightly higher, the universe would have had a positive curvature and would have recollapsed in on itself long ago. If it had been slightly lower, it would have had a negative curvature and would have expanded so rapidly that no structures like galaxies could have formed. The long, stable, structure-filled history of our universe depends on this incredible initial precision. The most extreme example of all, as we've mentioned, is the cosmological constant, which we will explore in our next segment. This value, representing the energy density of empty space that drives the universe's accelerated expansion, appears to be fine-tuned to an almost unimaginable degree, a precision of 1 part in 10 to the power of 120. Physicist Roger Penrose has calculated that the odds of the universe's initial low-entropy state, a necessary condition for the arrow of time and complex structures, occurring by chance are even more remote, on the order of 1 in 10 to the power of 10 to the power of 123. These numbers are so vast that they defy any intuitive grasp. So what are we to make of this collection of cosmic coincidences? This is where the profound mystery lies. The skeptic might argue that we are engaging in a form of anthropic bias, only noticing the conditions necessary for our own existence and imbuing them with undue significance. They might also argue that a future, more fundamental theory will show that these values are not coincidental at all, but are mathematically necessary. However, in the absence of such a theory, we are left with a universe that looks, for all the world, like a conspiracy to produce life. The mindfuck of the fine-tuning problem is that it pushes the limits of scientific explanation and opens the door to philosophical and metaphysical speculation. It forces us to confront the possibility that the universe is either vastly larger than we can see, the multiverse, the product of an intelligence, a designer or simulator, or the result of a statistical improbability so immense that it beggars belief. None of these options is entirely comfortable or scientifically verifiable at present. We are faced with a profound puzzle at the very heart of our scientific understanding of the cosmos. As you continue to fall asleep, let your mind contemplate the delicate balance of the cosmos. A universe standing on a knife's edge of physics. Imagine a control panel with dials for gravity, the strong force, the mass of the neutron, and see how the slightest nudge of any dial would cause the entire universe to dissolve into a simple, lifeless state. Acknowledge the profound, almost unbelievable precision that allows for the existence of stars, planets, chemistry, and your own conscious being. Let this sense of radical improbability wash over you. Find deep relaxation not in an explanation, but in the awe of the mystery itself, in the profound wonder of inhabiting a cosmos so exquisitely, so improbably, and so beautifully suited for your own existence, resting peacefully, a product of a cosmic coincidence of unimaginable scale. The cosmological constant problem explained. Having marveled at the general fine-tuning of the universe, let us now focus our attention on the most extreme, the most baffling, and the most profoundly mysterious example of this cosmic balancing act. We delve into what physicists have called the worst theoretical prediction in the history of physics. This is the cosmological constant problem. It concerns the energy of empty space itself, the energy of the vacuum, a concept that Einstein first proposed and which is now believed to be the driving force behind the universe's accelerating expansion, what we call dark energy. The mystery arises when we compare the theoretically predicted value of this energy with the value we actually observe. The discrepancy is not small. It is a colossal, almost comical mismatch of about 120 orders of magnitude. This is the largest, most spectacular failure of a theory ever encountered in science. To say the universe is fine-tuned in this regard is an understatement of cosmic proportions. The cosmological constant problem is a deep mindfuck that questions our most fundamental understanding of quantum mechanics, general relativity, and the very nature of spacetime itself. Contemplating this ultimate cosmic coincidence can lead to a state of profound humility and deep relaxation, as the sheer scale of the mystery dwarfs all human concerns as you fall asleep. Let's begin by understanding the concept of the cosmological constant, which is often represented by the Greek letter lambda, lambda. When Einstein formulated his theory of general relativity, his equations suggested that the universe should be dynamic, either expanding or contracting. However, the prevailing view at the time was that the universe was static. To fix this, Einstein added a new term to his equations, a fudge factor he called the cosmological constant. This lambda term represented a kind of intrinsic energy density of space itself, a repulsive force that could counteract gravity and hold the universe in a static balance. Later, when Edwin Hubble discovered that the universe was in fact expanding, Einstein famously called the introduction of this constant his biggest blunder. However, the story has a twist. In 1998, astronomers studying distant supernovae made the shocking discovery that the universe's expansion is not slowing down, but accelerating. There is a mysterious anti-gravitational force pushing spacetime apart. Suddenly, Einstein's blunder looked like a stroke of genius. The cosmological constant, or something very much like it, was resurrected as the leading candidate for this mysterious dark energy. The value of this constant, as measured by our best cosmological observations, is very, very small, but it is not zero. It is a tiny positive number that is gently but relentlessly driving the cosmic acceleration. The problem arises when we try to calculate what the value of this vacuum energy should be from our other great theory of reality, quantum field theory. According to quantum mechanics, empty space is not empty at all. It is a seething, bubbling cauldron of quantum foam, with virtual particles and antiparticles constantly popping into and out of existence. All of these fleeting virtual particles possess energy. When physicists try to sum up the total energy of all these quantum fluctuations in a given volume of empty space to predict the value of the cosmological constant, the result is an unmitigated disaster. The predicted value is about 10 to the power of 120 times larger than the value we actually observe. Let's try to put this number into perspective, though it is almost impossible. 10 to the power of 120 is a 1 followed by 120 zeros. It is a number so vast that if you tried to write it out, with every zero being the size of a proton, the entire observable universe would not be large enough to contain it. The discrepancy between the theoretical prediction and the observational measurement is the most colossal mismatch between theory and experiment in the history of science. It means that, for some reason we absolutely do not understand, the actual energy of the vacuum is either being cancelled out by some other unknown effect with an absurd, incomprehensible precision, or our fundamental understanding of quantum vacuum energy is catastrophically wrong. This is the cosmological constant problem, and it is a profound mystery. Why is the observed value so small? If it were as large as the theoretical prediction, its repulsive force would have been so immense that it would have ripped the universe apart in the first fractions of a second after the Big Bang. Stars, galaxies, and atoms would never have had a chance to form. For a universe like ours to exist, the predicted enormous vacuum energy and some other, currently unknown, effect must have cancelled each other out to a precision of 120 decimal places, leaving behind only the tiny, delicate residue that we observe today as dark energy. This is the ultimate example of fine-tuning. It's like finding a pencil perfectly balanced on its tip for billions of years. What are the possible solutions to this profound paradox? They are all deeply speculative. Perhaps there is a yet undiscovered principle of nature, a new kind of symmetry that forces the vacuum energy to be zero, and the tiny value we see is due to some other new field like quintessence. Perhaps our methods for calculating the vacuum energy in quantum field theory are fundamentally flawed. Some theories, like supersymmetry, were hoped to solve the problem by having different types of particles whose vacuum energy contributions would naturally cancel each other out, but experiments like those at the Large Hadron Collider have so far failed to find evidence for the simplest forms of supersymmetry. This is where anthropic reasoning and the multiverse come into play. If there is a multiverse where different bubble universes have different values for the cosmological constant, then the vast majority of these universes would be uninhabitable, either recollapsing instantly or flying apart too quickly. Only in the extremely rare universes where the vacuum energy, by sheer chance, cancelled out to this incredible degree of precision would observers like us be able to evolve. We observe this tiny value because we could not have existed to observe any other. In this view, the problem is solved by observer selection. The simulation hypothesis offers its own elegant, if equally speculative, solution. The fine-tuning of the cosmological constant is not an accident, but a parameter that was deliberately set by the simulators to that specific life-permitting value. They simply coded it into the physics engine of our reality. The cosmological constant problem is a testament to the immense gaps that still exist in our fundamental understanding of the cosmos. It lies at the turbulent intersection of our two best theories, general relativity and quantum mechanics, and signals that a deeper, unified theory is desperately needed. It is a mindfuck of the highest order, a number so wrong, so precisely wrong, that it hints at either a profound new principle of nature or a selection effect of cosmic proportions. As you continue to fall asleep, let your mind try to grasp the scale of this mystery. Imagine the immense, seething energy predicted to exist in every cubic centimeter of empty space, and then imagine a cosmic force that cancels it out with near-perfect precision, leaving only a whisper of energy behind, a whisper that is now gently accelerating the expansion of our entire universe. Acknowledge that this is the deepest and most embarrassing puzzle in modern physics, a profound sign of our own ignorance. Find deep relaxation not in an answer but in the sheer humbling scale of the unknown. Let the cosmic coincidence of the cosmological constant dissolve any sense of human arrogance. Resting peacefully in the quiet, dark energy that pervades all of space, a silent testament to the vast, beautiful, and utterly perplexing universal order. The weak anthropic principle. Having been confronted with the staggering improbability of the fine-tuning problem, let us now explore the most direct, scientific, and perhaps least speculative attempt to resolve it. This is the weak anthropic principle, WAP. The principle itself sounds deceptively simple, almost like a tautology or a trivial statement, but its implications are profound and have a major impact on how we interpret our place in the cosmos. The weak anthropic principle states that the observed properties of the universe must be compatible with the existence of a conscious, carbon-based life form like us to observe them. In other words, we find ourselves living in a universe that is capable of supporting life precisely because if it weren't, we wouldn't be here to wonder about it. This is not a statement about design or purpose. It is a statement about a fundamental observer selection bias. It is a crucial intellectual tool for understanding which features of the universe require a deep physical explanation, and which are simply a necessary precondition for our own existence. Contemplating this principle is a mindfuck that questions the very significance we attach to our own existence, inviting deep relaxation through a humbling recontextualization of our place in the grand scheme of things as you fall asleep. Let's unpack this with a simple analogy. Imagine you wake up and find yourself on a beautiful, life-sustaining planet with liquid water, a breathable atmosphere, and a stable star. You might be tempted to exclaim, "This is a miracle. What are the odds that I should find myself on one of the rare planets in the universe with conditions perfect for life?" The weak anthropic principle gently corrects this line of reasoning. It points out that you could not have found yourself on a planet without these conditions. Your very existence as a conscious, breathing observer automatically filters out all the lifeless planets. You are not observing a random sample of all planets. You are observing a sample that is heavily biased by the fact that you must exist on one of them. The fact that Earth is life-permitting is not a surprising coincidence that needs a special explanation beyond the fact that we are here. It is a necessary precondition for the observation itself. Now, let's apply this same logic to the entire universe. When we observe that the fundamental constants of physics, like the strength of gravity or the mass of the neutron, are exquisitely fine-tuned for life, we might be tempted to see this as a miracle demanding an explanation of design or purpose. The weak anthropic principle, however, suggests that we are making the same logical error. We are conscious observers asking why the universe is so well suited for conscious observers. The principle reminds us that if the universe were not fine-tuned in this way, we would not exist to ask the question. Our existence itself selects for a universe with these specific life-permitting properties. This is where the connection to the multiverse hypothesis becomes crucial. By itself, the weak anthropic principle doesn't have much explanatory power if there is only one universe. If there was only one cosmic lottery ticket ever printed, and it happened to be the winning one, that would still be an astonishing coincidence that cries out for explanation. But if, as many cosmological theories like eternal inflation suggest, there exists a multiverse, a vast, perhaps infinite ensemble of other universes, each with randomly different physical constants, then the WAP becomes an incredibly powerful explanatory tool. In a multiverse, the vast majority of universes would have constants that are not right for life. They would be sterile, empty, or fleeting. But, purely by statistical chance, A small fraction of these universes would happen to have the lucky combination of constants required for complexity and consciousness to emerge. The weak anthropic principle then explains why we find ourselves in one of these rare, hospitable universes. It's not because our universe is special in a design sense, but because it is special in a statistical sense. It is one of the few that could produce observers. The fine-tuning is thus explained as a combination of observer selection bias within a vast, unobservable cosmic landscape. We are simply living in our winning universe. The mind-fuck of the weak anthropic principle, especially when combined with the multiverse, is its radical decentering of humanity. It takes the very evidence that seems to point to our own special importance, the fine-tuning of the universe for our existence, and turns it on its head, using it to argue that we are likely just one of an infinite number of random outcomes, and our perceived specialness is a cognitive illusion created by selection bias. It suggests that our entire cosmic home, with its elegant laws and beautiful structures, might be nothing more than a statistical inevitability in a vast, indifferent multiverse. It questions our deep-seated intuition to find purpose and significance in the order of the cosmos. It's important to be clear about what the WAP is not. It is not a scientific theory in itself. It does not make falsifiable predictions. It is a philosophical principle of reasoning, a way to correct for certain types of observational bias. It cautions us against over-interpreting evidence that is a precondition of our own ability to gather that evidence. For example, we shouldn't be surprised to find that we live on a carbon-rich planet, as carbon is essential for our form of life. This requires no deep explanation beyond the fact of our existence. However, the WAP does not and cannot explain why the laws of physics are what they are, or why a multiverse, if it exists, has the properties it does. It simply provides a framework for understanding our particular place within that larger structure, whatever it may be. Critics of anthropic reasoning sometimes argue that it is a lazy explanation, a way of giving up on the search for a deeper, more fundamental physical reason for the values of the constants. They argue that we should continue to search for a theory of everything that might show that the constants must have the values they do, rendering the anthropic explanation unnecessary. This remains a key debate in theoretical physics and the philosophy of science. Is the fine-tuning a problem to be solved by better physics, or by better philosophical reasoning about observer effects? As you continue to fall asleep, gently hold the concept of observer selection bias in your mind. Picture a vast cosmic ocean of all possible universes, most of them stormy, chaotic, and lifeless, and see yourself awakening on the shore of a single calm, life-bearing island. Is your island's existence a miracle? Or is it simply the only kind of island you could ever possibly wake up on? Let the weak anthropic principle gently dissolve your sense of cosmic specialness. Find deep relaxation in this humbling yet strangely liberating perspective. The fact that the universe is fit for you is not a sign that it was made for you, but simply a precondition of you resting peacefully, a conscious observer in a universe that is, by necessity, capable of being observed. The strong anthropic principle. We have just explored the weak anthropic principle, a cautious, scientific principle of observer selection bias. Let us now venture into its far more controversial, speculative, and philosophically explosive sibling, the strong anthropic principle, SAP. While the weak principle states that the universe's observed properties must be compatible with our existence, the strong principle makes a much more radical and mind-bending claim. In one of its most famous formulations by physicists John Barrow and Frank Tipler, the SAP states, "The universe must have those properties which allow life to develop within it at some stage in its history." This is no longer a simple statement about selection bias. This is a powerful, seemingly teleological claim about the very nature of the cosmos itself. It suggests that the universe is not just accidentally life-permitting, but that it is, in some deep and mysterious way, compelled or required to bring forth conscious observers. This is a profound mindfuck that questions the very nature of causality and purpose in the cosmos, blurring the line between physics and metaphysics, and suggesting that our existence might be a necessary outcome of the universe's fundamental laws. Let us gently contemplate the staggering implications of a universe that must give rise to minds as you fall asleep. The strong anthropic principle takes the same data of fine-tuning that we've been exploring, but instead of explaining it away as a selection effect in a multiverse, it takes it at face value as evidence of a deep, underlying principle governing reality. It rejects the idea that our life-permitting universe is a mere cosmic accident. Instead, It posits that the emergence of consciousness is somehow written into the fabric of the universe from the very beginning. The laws of physics are not just a random set of rules that happen to be right for us. They are the right rules because the universe, in some sense, had to evolve observers. The implications of this are staggering and lead in several different philosophical directions. The first and most obvious interpretation is a theological one. The SAP can be seen as a modern, scientific restatement of the classical teleological argument, or the argument from design. If the universe must have properties that allow for life, it is a short step to conclude that it was designed that way by a purposeful creator. In this view, the simulators of the simulation hypothesis or the God of classical theology would be the mechanism that ensures the SAP holds true. The universe is compelled to have observers because its creator intended it to have observers. For many, the SAP is the most powerful piece of scientific evidence pointing towards a grand design. However, there are other non-theistic interpretations that are even more strange and mind-bending. One, often associated with the physicist John Archibald Wheeler, is the Participatory Anthropic Principle, PAP, which we will explore in its own segment but must touch upon here. This is the radical idea that observers are not just a final product of the universe, but are necessary for the universe's very existence in a concrete form. Drawing on some interpretations of quantum mechanics, this view suggests that a universe without conscious observers to collapse the quantum wave functions would remain a superposition of all possible histories, a ghostly realm of unrealized potential. It is only through the act of observation that the universe is brought into definite being. In this view, the universe must give rise to observers because observers are required to make the universe real in the first place, through a kind of vast, retroactive causal loop. We are not just inhabitants of the universe, we are, in a sense, its co-creators. Another possible interpretation is that there is a yet undiscovered law of nature, a deep principle of complexity or cosmic evolution, that guides the universe towards the formation of life and intelligence. Just as gravity dictates the formation of stars and galaxies, perhaps this unknown law dictates the emergence of complexity, consciousness, and observers as a natural and necessary outcome of the cosmic process. This would be a form of natural teleology, a purposefulness embedded in the laws of physics themselves, without requiring a conscious designer. The universe, in this view, is inherently self-organizing and self-actualizing, with consciousness as its ultimate goal or highest expression. This is a deeply spiritual, yet potentially naturalistic view of the cosmos. The mindfuck of the strong anthropic principle is its direct challenge to the Copernican principle, which has been a cornerstone of science since the Renaissance. The Copernican principle states that humanity does not occupy a privileged or special position in the universe. The SAP in all its forms suggests the opposite, that our position as conscious observers is not just special, but is in some way central to the structure or purpose of the universe itself. It places consciousness back at the heart of the cosmic drama, not as a trivial accident, but as a necessary and defining feature. Of course, the strong anthropic principle faces enormous criticism. It is, by its very nature, highly speculative and likely unfalsifiable. How could we ever prove that the universe must have the properties it does? It is often criticized as being unscientific, a philosophical or metaphysical statement masquerading as a physical principle. It can be seen as an argument from ignorance. Just because we don't yet have a fundamental theory that explains the constants, we posit a teleological principle to fill the gap. Many scientists are deeply uncomfortable with its teleological, purpose-driven language, seeing it as a step backwards from the objective, non-purposeful explanations that have been so successful in science. Yet, the principle refuses to go away because the fine-tuning it seeks to explain is a real and stubborn fact of our observations. It serves as a placeholder for our profound lack of understanding about why the conditions of our existence are so improbable. It is the name we give to the deep suspicion that our presence in this universe is not just a random fluke. As you continue your journey into deep sleep, allow your mind to grapple with this immense and radical idea. The idea of a universe that is not indifferent, but is somehow aimed, from its very inception, at the creation of beings like you. A universe compelled to awaken to itself through your consciousness. Is this a sign of a divine plan? A hint of our own creative power in shaping reality? Or the signature of a yet undiscovered law of cosmic evolution? Let go of the need for a definitive answer. Find deep relaxation in the sheer awe of this possibility, in the profound mystery of a cosmos that seems to have a place for you, a universe that is not just a stage for existence, but is in some way about existence. Resting peacefully, feeling yourself not as a cosmic accident, but as a necessary and deeply mysterious part of the universal order. The participatory anthropic principle. Having contemplated the bold claim of the strong anthropic principle, that the universe must give rise to observers, let us now explore its most radical, most perplexing, and most profoundly mind-bending variant. This is the participatory anthropic principle, PAP, a concept most famously associated with the visionary physicist John Archibald Wheeler. The PAP takes the connection between the observer and the cosmos to its ultimate, logic-defying conclusion. It suggests that conscious observers are not merely a final product of cosmic evolution, but are, in a bizarre, retroactive sense, necessary for the very existence of the universe's history. Drawing on the deepest and strangest aspects of quantum mechanics, this principle proposes that the universe in its early state existed only as a vast, ghostly superposition of all possible histories, a cloud of unrealized potential. It is only through the act of observation, performed by conscious beings like us billions of years later, that one of these histories is selected, collapsed, and brought into concrete, tangible reality. This is a staggering mindfuck that questions the very nature of time, causality, and our role in the cosmos. It suggests that we are not just inhabitants of the universe, but participants in its creation. Let the paradox of a universe that requires an audience to become real gently expand your sense of existence as you fall asleep. To begin to grasp this strange idea, we must return to the quantum measurement problem. As we've explored, quantum systems exist in a state of superposition, a probabilistic blur of all possible states, until a measurement is made, at which point the system collapses into a single, definite state. The observer effect shows that the act of observation is inextricably linked to the state of reality at the quantum level. Wheeler took this principle and applied it on a cosmic scale. If quantum mechanics is the fundamental theory of reality, then the entire universe in its infancy must have also been a quantum system. Therefore, the early universe must have existed in a grand superposition of all possible evolutionary paths, all possible sets of physical laws, all possible histories. Wheeler's famous thought experiment to illustrate this is the delayed choice experiment. It is a variation of the classic double-slit experiment, where a single particle seems to choose whether to act like a wave or a particle depending on how it is measured. Wheeler's version showed, both in theory and later in real experiments, that the choice of what to measure can be delayed until after the particle has already passed the point where it supposedly made its decision. The measurement we make now seems to reach back in time to influence the past state of the particle. Wheeler extrapolated this to the cosmos. He imagined light from a distant quasar traveling for billions of years, its path bent by a massive galaxy in between, creating two possible routes to Earth. We, as observers on Earth, can choose now how to set up our telescopes. We can set them up to determine which specific path the photon took, a particle measurement, or we can set them up to observe the interference pattern created by the photon taking both paths at once, a wave measurement. The choice we make in the present moment, Wheeler argued, determines the reality of the photon's multi-billion-year-old history. This leads to the core of the participatory anthropic principle. The universe evolves as a quantum system, a vast cloud of potentialities. Over billions of years, through processes like cosmic evolution, life and eventually consciousness emerge on a planet like Earth. This conscious observer then looks out at the cosmos, performs measurements, studies the cosmic microwave background, and observes the universe's history. According to Wheeler, this act of observation, this glance back at the early universe, is the measurement that collapses the grand cosmic superposition. It is the act that selects one definite history from all the infinite possibilities and makes it real, all the way back to the Big Bang. In this breathtaking vision, the universe and the observer are locked in a self-creating loop. The universe gives rise to conscious observers, and conscious observers, through their acts of measurement, give a concrete, historical reality to the universe. We are, in Wheeler's words, participants in bringing into being not only the near and here but the far away and long ago. The existence of the universe's past, in a definite form, is contingent on the existence of observers in its future. The mindfuck here is its radical re-envisioning of causality and time. It suggests a form of retrocausality, where the present can influence the deep past. It is not that we change the past, it is that we make the past definite. It's a universe that, in a sense, waits for a conscious participant to look back at it in order to solidify its own history. This questions everything we assume about the linear, forward flow of time and cause and effect. It suggests a holistic, self-synthesizing cosmos where the beginning and the end are inextricably linked through the act of conscious observation. This principle, of course, is highly speculative and resides on the very edge of theoretical physics and philosophy. It relies on a specific and by no means universally accepted interpretation of quantum mechanics, a form of the Copenhagen interpretation. Many physicists would favor the many-worlds interpretation, which would say that all possible cosmic histories are real in their own parallel universes, and our observation simply determines which branch we are on, without any retrocausality. Other physicists would argue that measurement does not require a conscious mind, but merely a macroscopic, decohering interaction, thus removing the special role of consciousness. However, the participatory anthropic principle remains a powerful and coherent, if deeply strange, philosophical possibility. It provides a potential, though non-traditional, explanation for the fine-tuning of the universe. The universe has the properties it does because these are the properties consistent with the universe eventually giving rise to observers who, in turn, make those properties real. Only a universe capable of producing consciousness could ever be actualized from the sea of quantum possibilities. As you continue to fall asleep, let your mind hold this strange and wondrous cosmic loop. Picture the early universe as a shimmering, ghostly fog of all possible histories, and see your own conscious awareness here and now as a single point of light that reaches back through billions of years, causing one of those histories to crystallize into a definite, solid past. Contemplate the paradox of being both a late-coming product of the universe and a necessary participant in its creation. Let go of the simple linear view of time and causality. Find deep relaxation in this radical vision of a participatory cosmos. A universe that perhaps requires an audience to truly exist, resting peacefully not just as a spectator of the cosmic drama, but as a silent, essential, and profoundly mysterious co-creator of reality itself. The final anthropic principle, Tipler. Having explored the strange participatory role of the observer in shaping the past, let us now journey to the other end of time, to the far future, to contemplate the most speculative, ambitious, and frankly bizarre of all the anthropic principles. This is the final anthropic principle FAP, proposed by the physicist and cosmologist Frank J. Tipler. While the weak and strong principles deal with the conditions necessary for life to arise, the FAP deals with the conditions necessary for intelligent life to never die out. It is a principle of cosmic eschatology, a theory of the ultimate fate of information and consciousness in the universe. The FAP states, intelligent information processing must come into existence in the universe, and once it comes into existence, it will never die out. This is a staggering claim, an assertion of mandatory cosmic immortality for intelligence itself. It is a mindfuck that combines cosmology, computation, and theology into a controversial and mind-expanding vision of the end of time, questioning the very nature of life, God, and the ultimate purpose of existence. Let this vision of an infinite future guide you into a state of profound cosmic relaxation as you fall asleep. To understand the FAP, we must first understand Tipler's concept of the omega point. Drawing on ideas from cosmology and computer science, Tipler envisioned a possible future for the universe. He assumed the universe is closed, meaning it has enough mass to eventually stop expanding and recollapse in on itself in a final big crunch. In the final moments of this collapse, Tipler argued, the energy and computational resources available would become infinite. He proposed that intelligent life, if it had managed to survive and spread throughout the cosmos, could harness this infinite computational capacity to run a perfect, infinite simulation of the entire history of the universe. This final, ultimate state of cosmic computation, containing all possible experiences and knowledge, is what he called the omega point. The omega point would be, in a sense, a godlike entity. It would be omniscient, as it would contain a perfect simulation of every event that has ever happened in the universe's history. It would be omnipotent, as it would control the entire computational resources of the collapsing cosmos. And it would be omnipresent, existing everywhere in the final state of spacetime. The final anthropic principle is the assertion that the laws of physics must be such that this omega point is an inevitable outcome. The universe, in Tipler's view, is structured from the beginning to ensure the eventual emergence of this ultimate computational consciousness. The most startling implication of the omega point theory is its vision of a technological afterlife. Tipler argued that the infinite computational power of the omega point would be used to resurrect, in perfect fidelity, every single conscious being that has ever lived in the history of the universe. This would be achieved by creating a perfect simulation of their existence, a point-for-point emulation of their life. You, me, everyone who has ever lived, would be brought back to life as a simulation within the mind of this final cosmic supercomputer, to live forever in a kind of computational heaven. This is how intelligence, once it arises, would never die out. Our immortality is guaranteed by the future physics of the universe's end. This is a breathtaking and profoundly strange vision. It takes the simulation hypothesis and places it not at our origin, but at our ultimate destination. We are not in a simulation now, according to Tipler, but we are destined to be perfectly simulated in the future. It's a form of physical eschatology, a scientific theory of the Last Judgment and the resurrection of the dead. The mindfuck of the final anthropic principle is its complete fusion of hard science fiction, theoretical physics, and religious concepts. It attempts to provide a purely physical, albeit highly speculative, mechanism for achieving outcomes that have traditionally been the domain of faith. It questions the very boundaries between science and religion. God, in this model, is not a transcendent creator at the beginning of time, but an emergent computational entity at the end of time, a being that we, as intelligent life, will ultimately evolve into and become part of. The purpose of existence, in this view, is to contribute our information, our experiences, to the final, omniscient mind of the omega point. The final anthropic principle and the omega point theory have been met with widespread criticism and skepticism from both the scientific and philosophical communities. The scientific objections are numerous. The core assumption that the universe is closed and will recollapse is contrary to our current best evidence, which points towards an eternally accelerating expansion, the Big Freeze scenario driven by dark energy. Tipler has proposed ways in which a collapsing scenario might still be possible, but it is not the standard cosmological model. Furthermore, the claim that the computational resources in a collapsing universe would become infinite is highly debated and may not hold up to rigorous physical scrutiny. The entire theory is, by its nature, unfalsifiable and highly speculative, a grand edifice built upon a chain of unproven, and in some cases unlikely, assumptions. The philosophical and theological objections are also strong. Many theologians find the idea of a God, who is not the creator, but a future, emergent product of the universe, to be a profound departure from traditional concepts of the divine. Philosophers question whether a perfect simulation of a person is truly the same person, the paradox of identity, and whether a simulated afterlife constitutes genuine survival. The theory can be seen as a form of ultimate technological utopianism, a scientific myth that provides comfort but lacks a solid foundation. Despite the criticism, the FAP remains a fascinating and powerful thought experiment. It represents one of the most ambitious attempts ever made to construct a complete, teleological, and physically grounded theory of everything, from the beginning of the universe to its ultimate purpose and end. It serves as a powerful example of how the human mind, when grappling with the concept of infinity, can generate narratives of immense scope and imagination. It pushes the boundaries of what we consider a scientific theory and forces us to confront our deepest desires for meaning, permanence, and immortality. As you continue to fall asleep, let your mind drift into the impossibly distant future. Imagine the universe not expanding into cold darkness, but collapsing back in on itself, into a final, infinitely hot and energetic point. And imagine, within that final moment, an intelligence of infinite capacity, an omega point recreating the entire history of the cosmos in a perfect simulation. Recreating you in this very moment. Contemplate this strange vision of a technological resurrection, a physical basis for eternal life. Let go of the need to believe or disbelieve this speculative tale. Find deep relaxation in the sheer, boundless creativity of the human mind to grapple with the ultimate questions of existence and its final purpose, resting peacefully, a single point of data in a cosmic story that is, perhaps, destined to be told forever. The multiverse as a solution to fine-tuning. We have been haunted throughout our cosmic journey by the mystery of fine-tuning, the staggering, improbable fact that the fundamental constants of our universe are perfectly balanced to allow for the existence of life. We have explored solutions that posit a purpose or a design, like the strong anthropic principle or the simulation hypothesis. Let us now turn to the leading and in many ways most scientifically mainstream, naturalistic explanation for this profound cosmic coincidence. This is the multiverse hypothesis. It is the idea that our universe is not the only one, Instead, it is just one of countless, perhaps even an infinite number of other universes, each with its own set of physical laws and constants. The multiverse, in this context, is not just a science fiction trope, but a potential consequence of some of our most advanced theories in physics, like string theory and eternal inflation. As a solution to fine-tuning, it is both elegantly simple and metaphysically staggering. It is a mind-fuck that questions the very uniqueness of our cosmos and our existence, suggesting that our seemingly special world is just one lucky ticket in an infinite cosmic lottery. Let the idea of these other worlds gently expand your sense of reality as you fall asleep. The logic behind the multiverse as a solution is a powerful application of the weak anthropic principle, which we explored earlier. The weak anthropic principle states that our existence as observers biases what we see. We must, by necessity, find ourselves in a universe with life-permitting conditions. By itself, if our universe is the only one, this principle doesn't explain much. It just states a consistency. It doesn't explain why the one and only universe is so lucky. But if there is a multiverse, the situation changes dramatically. Imagine a cosmic universe generator that produces a vast ensemble of universes. In most of these universes, the dials of the physical constants are set to random values. As we've seen, the vast majority of these settings would result in sterile, lifeless universes. One universe might collapse in on itself in a fraction of a second. Another might expand so rapidly that no matter could ever clump together to form stars. Another might have laws that don't allow for stable chemistry. These universes would exist, but they would be empty of observers. However, in this vast collection, purely by the laws of chance, a very small number of universes will happen to have their constants fall within the incredibly narrow life-permitting range. They will be the lucky ones, the winners of the cosmic lottery. And since conscious observers can only evolve in these lucky, fine-tuned universes, it is an absolute certainty that we would find ourselves living in one of them. The fine-tuning of our universe is therefore explained not as a miracle or a design, but as a simple selection bias. We are here discussing the fine-tuning because we are, by definition, in a universe where the conditions allowed us to be here. All the residents of all the other lifeless universes are not having this conversation. The apparent improbability of our universe is an illusion created by our failure to consider all the other failed universes. This is a powerful and elegant naturalistic explanation. It requires no new principles of purpose or design. It simply requires accepting the existence of other universes. The crucial question then is, are there good scientific reasons to believe a multiverse might actually exist? The answer tentatively is yes. The multiverse is not just an ad hoc idea invented to solve the fine-tuning problem. It appears as a natural, almost unavoidable consequence of some of our leading theories in physics. One of the most prominent sources for the multiverse idea is eternal inflation. According to the theory of cosmic inflation, our entire observable universe was born from a tiny patch of space that underwent a period of hyper-accelerated expansion in the first moments after the Big Bang. The theory of eternal inflation suggests that this inflationary process, on a larger scale, might be happening forever. While inflation stops in certain pockets, creating stable bubble universes like our own, the space between these bubbles continues to inflate wildly, spawning new bubble universes in a never-ending, self-reproducing process. This would create an infinite fractal multiverse of bubble universes, each of which could potentially cool down with different physical properties, providing the vast ensemble needed for the anthropic explanation to work. String theory, a candidate for a theory of everything, also points towards a multiverse. String theory requires the existence of extra hidden dimensions of space. The specific way these extra dimensions are curled up and compactified determines the effective laws of physics and the values of the constants in our observable 3D world. The theory suggests there might be a vast number of ways for these dimensions to be stabilized, perhaps 10 to the power of 500 or even more. Each stable configuration would correspond to a different vacuum state, a different pocket universe, with its own set of physical laws. This is the string theory landscape. Our universe would be just one of these many possible valleys in the landscape, and we live in this one because its specific laws happen to be suitable for life. The mindfuck of the multiverse is its radical re-envisioning of what universe means. It suggests that our entire cosmos, everything we can ever see or interact with, might be just one insignificant bubble in an infinitely vast and diverse cosmic foam. It questions our uniqueness and the ultimate significance of our physical laws. The laws of our universe might not be the one true set of laws, but just the local bylaws of our particular cosmic patch. It is a vision of reality that is unimaginably larger and stranger than anything our ancestors could have conceived. Of course, the multiverse hypothesis is profoundly controversial. The primary objection is that it is, at least for now, unfalsifiable. By definition, these other universes are causally disconnected from ours. We can never travel to them, see them, or receive any direct experimental evidence of their existence. The hypothesis is a purely theoretical inference. Critics argue that it is unscientific, a form of metaphysical speculation that posits an infinite number of unobservable entities to explain our one observation. They argue it violates Occam's razor by multiplying entities without necessity. Proponents, however, argue that the multiverse is a direct prediction of our best physical theories, and that to deny it would require adding a new, unproven principle that forbids other universes from existing. As you continue to fall asleep, allow your mind to expand to the scale of the multiverse. Picture our universe as a single shimmering bubble, and then imagine an endless ocean of other bubbles, each one a different cosmos, with different laws, different colors, different fates. Most of them empty, but a few, like ours, teeming with the possibility of life. Let go of the feeling that our universe is all there is. Find deep relaxation in this vast, humbling perspective. The fine-tuning of our world is not a paradox to be solved, but a simple consequence of our own existence in a single habitable world among countless others. Rest peacefully, a citizen of your universe, floating calmly in the grand, silent, and profoundly mysterious ocean of the multiverse. String theory landscape. Having contemplated the multiverse as a potential solution to the profound mystery of cosmic fine-tuning, let us now delve into one of the most significant, though highly speculative, theoretical frameworks in modern physics that provides a concrete physical basis for such a vast ensemble of universes. We enter the abstract and beautiful world of string theory, and specifically, the concept of the string theory landscape. For decades, string theory was pursued with the hope that it would be a unique theory of everything, a single, elegant set of equations that would prove our universe's laws and constants are the only ones that are mathematically possible. However, the theory evolved in an unexpected direction. Instead of predicting a single universe, it seems to predict a colossal number of possible universes, each with its own distinct physical properties. This vast collection of possible solutions is the string theory landscape. It is a profound mindfuck that transforms a theory of uniqueness into a theory of immense diversity, providing a potential physical mechanism for the multiverse and questioning the fundamental necessity of our own reality. Let the idea of a cosmic landscape of possibilities gently expand your mind as you fall asleep. To understand the string theory landscape, we must first touch upon the core idea of string theory itself. It is an ambitious attempt to unify the two pillars of modern physics: general relativity, our theory of gravity and the large-scale universe, and quantum mechanics, our theory of particles and forces at the smallest scales. String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, one-dimensional vibrating strings. The different elementary particles we observe, electrons, quarks, photons, are, in this view, just different vibrational modes of these fundamental strings, much like the different notes produced by a violin string are the result of its different vibrations. This is an incredibly elegant idea, promising to unify all of matter and forces into a single coherent framework, a cosmic symphony of vibrating strings. However, for the mathematics of string theory to be consistent, it requires a startling feature: the existence of extra hidden dimensions of space. In addition to the three spatial dimensions we experience, length, width, and height, and the dimension of time, string theory typically requires a total of 10 or 11 spacetime dimensions. This raises an immediate question. If these extra dimensions exist, where are they? The proposed answer is that they are compactified, curled up into tiny, intricate geometric shapes at every single point in our familiar space, on a scale so small, the Planck scale, that we can never directly perceive them. This is where the landscape emerges. The specific way these extra dimensions are curled up and folded, their geometry, or topology, is not unique. According to the theory, there is a vast number of different ways to compactify these extra dimensions, each one a stable, mathematically consistent solution to the theory's equations. Each of these different geometric solutions would result in a different set of effective physical laws in the large, three-dimensional world we experience. The vibrational modes of the strings, and thus the properties of the particles and forces they represent, would be different depending on the specific shape of the hidden dimensions. The strength of gravity, the charge of the electron, the number of particle families, all these constants of nature would not be fundamental, but would be determined by the local geometry of the compactified extra dimensions. This vast collection of possible solutions, of possible geometries for the extra dimensions, is the string theory landscape. The number of these possible stable configurations is estimated to be astronomically large, perhaps 10 to the power of 500 or even more. Each of these solutions represents a distinct vacuum state, a stable, self-consistent set of physical laws. Each of these vacuum states can be pictured as a valley in a colossal, multidimensional landscape of possibilities. Our universe, with its specific set of physical laws and constants, is just one of these countless valleys. This provides a concrete physical mechanism for the multiverse. In the context of a larger cosmological theory like eternal inflation, it's plausible that as new bubble universes are formed, they cool down and settle into different valleys in the string theory landscape, each one resulting in a universe with a different set of physical laws. The landscape provides the menu of possible universes, and eternal inflation provides the mechanism for manufacturing them. The mindfuck of the string theory landscape is profound. It represents a dramatic shift in the aspirations of fundamental physics. The original hope for a theory of everything was that it would yield a unique solution, proving that our universe must be the way it is for reasons of deep mathematical necessity. The discovery of the landscape suggests the opposite, that our universe's laws might be just one of an immense number of possibilities, a result of a historical, cosmological accident rather than a fundamental necessity. It changes the goal of physics from finding the equation to understanding the entire landscape of equations. It suggests that the fine-tuning of our universe for life is not a deep puzzle of necessity, but a simple consequence of us being located in one of the rare habitable valleys in this vast landscape of possibilities. The anthropic principle becomes the guiding principle for explaining our specific location within the landscape. This idea is, of course, deeply controversial. The string theory landscape is a mathematical consequence of the theory, but neither string theory itself nor the existence of these other valleys or universes has been empirically verified. It is a solution that lies purely in the realm of theoretical mathematics. Critics, sometimes referred to as string theory skeptics, argue that a theory that predicts 10 to the power of 500 different possible universes is not a predictive theory at all. It's a framework so flexible that it can explain almost anything, making it unfalsifiable and, in their view, unscientific. They argue that it gives up on the traditional goal of science, which is to provide unique, testable explanations for the world we observe. Proponents, on the other hand, argue that this is simply where the mathematics leads us, and we must follow it, even if it takes us to uncomfortable, counterintuitive places. They maintain that string theory is the most promising candidate for a theory of quantum gravity and that the existence of the landscape is one of its core predictions, one we must take seriously. The debate over the scientific status and philosophical implications of the string theory landscape is one of the most active and important in all of fundamental physics. As you continue to fall asleep, let your mind drift into this abstract, multidimensional space. Imagine a vast, rolling landscape of unimaginable scale, the string theory landscape, and see each valley in this landscape as a potential universe, a complete cosmos with its own unique laws of physics. Picture our own universe as just one of these countless valleys, a single sheltered place where the conditions happen to be just right for stars, planets, and consciousness to form. Let go of the idea that our reality is the only possible one. Find deep relaxation in the sheer, mind-expanding scale of this vision. A vision that explains our existence not through specialness or necessity, but through the simple logic of existing in one of the rare places where existence is possible, resting peacefully, a resident of one small valley in a potentially infinite and deeply mysterious cosmic landscape. The nature of physical laws. We have spoken of the laws of physics as the fundamental rules that govern our universe, the code of our reality. We have seen how their specific values appear to be fine-tuned for our existence. Let us now step back and ask an even more fundamental question. What are these laws? Are they eternal, transcendent, and logically inevitable truths about reality, existing in some platonic realm, that our universe must necessarily obey? Or are they merely contingent, descriptive regularities, bylaws, that just happen to apply to our specific cosmic patch, perhaps one among many in a multiverse? This mystery, the nature of physical laws, is a deep philosophical inquiry that questions the very foundation of cosmic order. It's a mindfuck that challenges our assumption that the world must be the way it is, and instead opens up the possibility that our entire reality is built upon a set of fundamentally arbitrary or accidental rules. Contemplating the status of these laws offers a path to deep relaxation by appreciating the profound contingency of our world as you fall asleep. Let's begin with the traditional and perhaps more intuitive view. This is the idea that the laws of physics are necessary and prescriptive. In this view, the laws are not just descriptions of how things behave, they are the reason things behave that way. They are like a kind of cosmic legislation that governs the universe. The law of gravity, in this sense, is not just a summary of how objects have fallen in the past. It is a command that dictates how objects will fall in the future. This perspective often aligns with a Platonic view of mathematics, suggesting that the elegant mathematical structures describing our laws are not just our inventions, but reflections of a deep, underlying, and unchanging logical order to the universe. Many physicists, driven by a desire for a unique and elegant theory of everything, implicitly subscribe to this view. Their hope is to one day discover a final theory so logically compelling and internally consistent that it will show that the laws of physics and the constants of nature could not have been any other way. In this picture, the universe is the way it is because it is the only way it can logically be. Our existence would be, in a sense, inevitable. However, a different and in some ways more modern perspective, often called the Humean or regularity theory of laws, proposes a radically different picture. This view, tracing back to the skepticism of philosopher David Hume, argues that the laws of physics are not prescriptive commands, but are merely descriptive summaries of the regular patterns we have observed in the universe. They are a concise and powerful way of describing the cosmic wallpaper of events. In this view, there is no mysterious force enforcing the law of gravity. There is simply a brute fact. All massive objects in the universe have, so far, consistently moved towards each other in a way that can be described by a specific equation. The law is our description of this pattern. It doesn't govern the pattern. This descriptive view has profound implications. If the laws are just descriptions of regularities, there is no logical guarantee that they must continue to hold in the future. This connects to Hume's problem of induction. And, more importantly for our inquiry, there is no reason to believe that these patterns are inevitable or necessary. The set of regularities that governs our universe could simply be a contingent, brute fact. The universe just happens to have these specific patterns, and it could have had others. This Humean, descriptive view of laws fits very naturally with the multiverse hypothesis and the string theory landscape. If there are countless other universes, each could have its own set of fundamental regularities, its own cosmic wallpaper. The laws of physics would no longer be universal and necessary, but local and contingent, the bylaws of our particular cosmic bubble. Our laws would be the way they are not because of logical necessity, but because of a historical accident of which bubble universe we happen to inhabit. This completely changes our understanding of the fine-tuning problem. The laws are not fine-tuned for us in a purposeful sense. We simply exist in one of the rare universes where the contingent laws happen to be life-permitting. The mindfuck here is the radical dethroning of physical law. It transforms the laws from eternal, godlike principles into mere local customs of our particular corner of existence. It questions the very idea of a theory of everything that would explain why the laws are what they are in a necessary sense. Instead, the ultimate answer might simply be, that's just the way things are here. It introduces a profound sense of contingency, of cosmic accident, at the very foundation of the universal order. This debate also connects to the simulation hypothesis. If our universe is a simulation, then the laws of physics are neither prescriptive Platonic truths nor descriptive summaries of brute facts. They are, as we've explored, the code of the simulation. They are prescriptive within the simulation, they govern how things behave, but they are contingent from the perspective of the simulators, who could have programmed them differently. In this case, the laws are a form of artificial necessity, rules imposed by a designer. So, what is the true nature of physical laws? Are they necessary truths waiting to be discovered? Are they descriptive summaries of contingent patterns? Or are they the programmed rules of an artificial reality? This mystery is one of the deepest in the philosophy of science. We have no way to step outside our universe to see if other laws are possible or if our laws are just descriptions. We are trapped within the system, trying to deduce the nature of the rules while playing the game. The search for a theory of everything is a bet on the idea that the laws are inevitable. The acceptance of the multiverse as an explanation for fine-tuning is a bet on the idea that the laws are contingent. The simulation hypothesis is a bet on the idea that the laws are artificial. Each of these positions represents a different philosophical stance on the nature of cosmic order, and we currently lack the evidence to definitively choose between them. As you continue to fall asleep, contemplate the laws that govern this very moment. The law of gravity that holds you gently in place. The laws of chemistry that govern the slow rhythm of your breath. The laws of thermodynamics that dictate the warmth of your body. Now ask yourself, are these laws necessary? Must they be this way? Or are they simply the local customs of our cosmos, contingent patterns in a vast sea of possibility? Let the question of the nature of physical laws gently dissolve your assumptions about a fixed and inevitable reality. Find deep relaxation in the profound mystery of cosmic governance. Whether our universe is a product of unbreakable logic, of random chance, or of deliberate code, its order is the very condition of our existence. Resting peacefully, floating calmly in a universe governed by laws whose ultimate status remains a beautiful, unanswered question. The role of symmetry in physics and cosmic order. As we continue our contemplation of the deep universal order, let us now explore one of the most powerful, elegant, and profoundly beautiful principles that guides our understanding of the cosmos: the concept of symmetry. In our everyday lives, we think of symmetry as a pleasing visual property: the balanced wings of a butterfly, the reflection of a mountain in a still lake, the six-fold pattern of a snowflake. But in modern physics, symmetry is a much deeper and more powerful concept. It is a guiding principle, a tool for discovery, and perhaps a fundamental clue to the underlying nature of reality itself. Many physicists believe that the most fundamental laws of physics are expressions of deep, underlying symmetries in the universe. The mystery is why the universe seems to be governed by these principles of elegance and harmony. Is the profound role of symmetry a hint of a grand design, a sign of an underlying mathematical reality, or a feature that simply makes a complex universe comprehensible to minds like ours? Contemplating the role of symmetry in the cosmos is a pathway to appreciating the hidden beauty and coherence of our existence, inviting deep relaxation through the perception of a deep, underlying harmony as you fall asleep. Let's begin by expanding our understanding of symmetry in physics. A physical system is said to have a symmetry if it remains unchanged or invariant after a certain transformation is applied to it. A simple sphere is rotationally symmetric. You can rotate it by any angle around its center, and it still looks exactly the same. This simple geometric idea is extended to the laws of physics themselves. For example, the laws of physics are translationally symmetric in space. This means that if you conduct an experiment here, and then move your entire laboratory 10 miles to the west and conduct the exact same experiment, you will get the exact same result. The laws of physics do not depend on your absolute location in space. They are the same everywhere. This seems obvious, but it is a profound symmetry of our universe. Similarly, the laws are rotationally symmetric. The outcome of an experiment does not depend on the direction your laboratory is pointing. And they are temporally symmetric, meaning the laws of physics are the same today as they were yesterday and as they will be tomorrow. The fundamental rules of the cosmos do not change over time. These basic spacetime symmetries are the foundation of our ability to do science. Without them, the universe would be a chaotic and unpredictable place where consistent experimentation would be impossible. The connection between symmetry and physical laws becomes even deeper and more profound with a mathematical theorem known as Noether's theorem, formulated by the brilliant mathematician Emmy Noether. This theorem is one of the most beautiful and important results in all of physics. It reveals a direct, one-to-one correspondence between the symmetries of a physical system and the conservation laws that it obeys. A conservation law is a rule stating that a particular physical quantity remains constant over time. Noether's theorem showed that for every continuous symmetry in the laws of physics, there is a corresponding conserved quantity. For example, the fact that the laws of physics are the same everywhere, translational symmetry, directly implies the law of conservation of momentum. The fact that the laws are the same regardless of orientation, rotational symmetry, directly implies the law of conservation of angular momentum. And the fact that the laws are the same at all times, temporal symmetry, directly implies the law of conservation of energy, one of the most fundamental principles in all of science. This is a breathtaking connection. The most basic conservation laws that govern the universe are not just arbitrary rules. They are the direct logical consequences of the symmetries of spacetime itself. The order and predictability of the cosmos stem from its underlying harmony and balance. Modern particle physics is built almost entirely on more abstract and complex principles of symmetry, known as gauge symmetries. The theories that describe the fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, collectively known as the Standard Model of particle physics, are all gauge theories. They are constructed by demanding that the equations remain invariant under certain abstract mathematical transformations. From these symmetry principles, physicists were able to predict the existence of fundamental particles, like the W and Z bosons and the gluon, long before they were discovered in experiments. The search for a theory of everything is, in many ways, a search for a single, larger, more elegant symmetry group that would unify all the known forces, including gravity. Physicists' deep faith in the principle of symmetry as a guide to truth has been one of the most successful research programs in the history of science. The mindfuck of the role of symmetry is its profound implication for the nature of reality. It suggests that the universe, at its most fundamental level, is not just a random collection of particles and forces, but is governed by principles of elegance, harmony, and beauty. It questions why this should be the case. Why is the universe comprehensible to us through the language of symmetry? Why are the most fundamental theories also often the most mathematically beautiful ones? This is where the mystery deepens and connects to our broader theme. One perspective is that this is powerful evidence of a grand design. A rational, intelligent creator, a cosmic artist or mathematician, would naturally build a universe based on elegant and harmonious principles. The beauty we find in the laws of physics could be a reflection of the mind of God. The universe is orderly because it is a deliberate creation. Another perspective, aligning with a form of mathematical Platonism, is that the universe is, in some deep sense, made of mathematics. The reason the laws are symmetrical and elegant is that they are simply reflecting the inherent symmetries and elegance of the underlying mathematical structures that constitute reality. The order is not imposed by a designer, it is an intrinsic property of the mathematical existence we inhabit. A more cautious, anthropic perspective might suggest a form of observer selection bias. Perhaps, in a multiverse, there are countless universes with ugly, asymmetrical, and chaotic laws. It might be that only in universes with sufficient symmetry and the resulting conservation laws are stable, complex structures, like galaxies, stars, and life, able to form and persist. A universe without conservation of energy, for example, might be too chaotic and unpredictable for life to ever get a foothold. We find ourselves in a beautiful, symmetrical universe because it is the only kind of universe that could produce observers capable of appreciating that beauty. Regardless of the ultimate explanation, the profound role of symmetry in shaping the universal order is undeniable. It is a secret of the cosmos that science has revealed, a secret that speaks of a deep coherence and elegance underlying the apparent complexity of the world. It is a principle that connects our aesthetic sense of beauty with the fundamental workings of reality. As you continue to fall asleep, let your mind gently hold the concept of symmetry. Picture the perfect balance of a snowflake, the elegant orbit of a planet, the deep harmony in a physical law. Contemplate the profound connection revealed by Noether's theorem, where the universe's stability and predictability, the conservation of energy and momentum, are born directly from its underlying symmetries. Let this idea dissolve any sense of the universe as a purely random or chaotic place. Find deep relaxation in the profound order that this principle reveals. Whether it is the signature of a designer, a feature of a mathematical reality, or a condition for our own existence, this cosmic harmony is the bedrock of our world, resting peacefully, floating calmly in a universe governed by a deep and beautiful, mysterious elegance. The unreasonable effectiveness of mathematics and science. Let us now contemplate a mystery that lies at the very heart of our ability to understand the universe, a phenomenon the physicist Eugene Wigner famously called the unreasonable effectiveness of mathematics in the natural sciences. The puzzle is this: why is it that mathematics, a discipline that often seems to be a pure, abstract creation of the human mind, a game played with symbols and logic in the realm of pure thought, is so astonishingly effective at describing and predicting the physical world? Why do the elegant equations and intricate structures devised by mathematicians in their studies, often with no thought of practical application, turn out to be the perfect language for describing everything from the motion of planets to the behavior of quantum particles? This profound correspondence between the inner world of human mathematical thought and the outer world of physical reality is a deep mind fuck, a cosmic coincidence so profound that it has baffled scientists and philosophers for centuries. It questions the very nature of truth, the structure of the universe, and the relationship between the human mind and the cosmos. Let this deep and wondrous resonance guide you into a state of deep relaxation as you fall asleep. Consider the history of this strange effectiveness. The ancient Greeks, particularly the Pythagoreans, believed that all things are number, that the cosmos was fundamentally a mathematical harmony. This idea fell in and out of favor, but was resurrected with astonishing power during the scientific revolution. Isaac Newton was able to describe the universal law of gravitation, governing both falling apples and orbiting moons, with a simple, elegant mathematical equation. Later, James Clerk Maxwell unified the seemingly separate phenomena of electricity, magnetism, and light into a single, beautiful set of equations, and in doing so, predicted the existence of radio waves. Albert Einstein, working primarily from principles of mathematical elegance and consistency, developed the theory of general relativity, which was only later confirmed by astronomical observations. The mathematics seemed to lead the way, revealing truths about the physical world before they were even observed. This pattern continues to the present day. Quantum mechanics, our most successful theory of the very small, is expressed in a highly abstract mathematical language involving wave functions, complex numbers, and Hilbert spaces. Paul Dirac predicted the existence of antimatter based on the mathematical beauty and symmetry of his equation for the electron. String theory, our current leading candidate for a theory of everything, is a field driven almost entirely by the exploration of incredibly complex and abstract mathematical structures, with the hope that they will eventually connect to and explain the physical reality we observe. Time and time again, abstract mathematical concepts, sometimes developed for purely aesthetic reasons, have turned out to be precisely the tools needed to describe the universe. As Wigner wrote, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve." So, why is mathematics so unreasonably effective? What is the solution to this profound mystery? There are several competing philosophical perspectives, each with its own profound implications. The first, as we have touched upon, is Platonism. This view holds that mathematical objects and structures are not human inventions, but are real, independently existing entities in an abstract, non-physical realm. In this view, the universe itself is also fundamentally mathematical in its structure. The reason our mathematical ideas match the physical world so well is because both the human mind, through the act of pure reason, and the physical world, through its inherent structure, are tapping into the same single, objective, and transcendent mathematical reality. The physicist is discovering the mathematical structure of the physical world, while the mathematician is exploring the structure of the abstract realm directly. Their findings align because they are both exploring different facets of the same underlying mathematical truth. In this view, the effectiveness of mathematics is not unreasonable at all. It is a direct consequence of living in a mathematical universe. A second perspective, in stark contrast, is anti-Platonism or nominalism. This view denies the existence of an independent realm of abstract mathematical objects. It sees mathematics as a human invention, a powerful and sophisticated language, or a formal game of symbols we have constructed. But if it is just a human invention, how do we explain its incredible effectiveness? One answer is evolutionary. It could be that our brains, and the logical and mathematical systems they are capable of creating, have evolved within this universe. Natural selection would have favored minds that were good at creating mental models that accurately reflected the world's underlying regularities. Our mathematics works so well because it is a product of a brain that was shaped by the very universe it seeks to describe. We are good at creating math that fits the world because evolution has made us good at it, a form of the Anthropic principle applied to our cognitive abilities. Another anti-Platonist argument is that we might be engaging in a form of selection bias. We tend to focus on the spectacular successes of mathematics and physics, but we might be ignoring the vast areas of abstract mathematics that have, so far, found no application in the physical world. Furthermore, science itself is a process of actively selecting the mathematical tools that work. Physicists try out many different mathematical approaches, and they keep the ones that successfully model the data and discard the ones that don't. The effectiveness of mathematics might therefore be less of a miracle and more of a result of this deliberate and sometimes difficult process of finding the right tool for the job from a very large toolbox of human inventions. The simulation hypothesis offers its own unique and tantalizing explanation. If our universe is a computation as we've explored, then it is not surprising at all that it is describable by mathematics. In fact, it would be a necessity. The underlying reality is a mathematical and computational structure. The laws of physics are the algorithm, and the language of algorithms is mathematics. The reason mathematics is so effective is that we are, in a sense, discovering the source code of our simulated reality. This provides a direct, if deeply strange, explanation for the deep mathematical nature of our cosmos. The mindfuck of the unreasonable effectiveness of mathematics is that it sits at the very heart of our scientific worldview, a fundamental philosophical puzzle that we cannot seem to solve. It questions the relationship between human thought and the external world. Is the order we find in the universe a reflection of an intrinsic cosmic logic, or is it a reflection of the inherent structure of our own minds? Are we discovering the universe's blueprint, or are we simply projecting our own mind's preferred language onto it? As you continue to fall asleep, let your mind gently hold this profound resonance between the abstract world of number and the physical world of stars and atoms. Contemplate the elegance of an equation that can describe the fall of an apple and the orbit of the moon. Is this a clue to a grand design? A sign of a multiverse where we evolved to fit our mathematical world? The signature of a simulation? Or a mystery that will forever lie at the boundary of human understanding? Find deep relaxation in the sheer beauty of this fact, regardless of its ultimate explanation. Appreciate the profound harmony between your own capacity for reason and the deep, logical structure of the cosmos. Resting peacefully within the mysterious, elegant, and deeply resonant symphony of mathematics and reality. Is the universe made of math? We have just contemplated the unreasonable effectiveness of mathematics in describing the physical world, the mysterious harmony between abstract thought and cosmic law. Let us now take this idea to its ultimate, most radical and profoundly mind-bending conclusion. What if the relationship is not one of description but of identity? What if the universe is not just describable by mathematics, but what if it is mathematics? This is the core of the mathematical universe hypothesis, MUH, most famously championed by cosmologist Max Tegmark. This hypothesis proposes that our physical reality is not just a physical structure, but is, in its deepest essence, a pure mathematical structure. In this view, there is nothing in the universe that is not ultimately mathematical. All of this stuff, of the world, particles, forces, spacetime, even consciousness, is ultimately reducible to numbers, relations, and geometric structures. This is a profound mindfuck that completely dissolves the distinction between the language of science and the substance of reality, questioning the very nature of existence itself. Is our physical world merely one department in the grand, timeless library of all possible mathematical structures? Let this ultimate abstraction gently expand your sense of what reality could be as you fall asleep. To understand this radical idea, we must first confront our intuitive prejudice for stuff. We are accustomed to thinking of the world as being made of physical substance. But modern physics has already been dissolving this intuition for over a century. A subatomic particle, like an electron, is not a tiny, solid billiard ball. It is better described by a set of mathematical properties: mass, charge, spin, and a wave function, a purely mathematical object that describes its probabilities. The physicality of the electron is entirely captured by its mathematical description. An electromagnetic field is not a physical substance in the traditional sense. It is a set of values, of vectors at every point in spacetime, again, a mathematical structure. Tegmark's hypothesis takes this trend to its logical conclusion. It proposes that if the description of a physical system is a mathematical structure, and that description captures all of its properties, then perhaps the system is that mathematical structure. There is no extra non-mathematical fire, or stuff, that the equations are written on. The equations are the reality. Tegmark calls this the external reality hypothesis, the idea that there exists an external physical reality completely independent of us humans. He then argues that if this is true, the ultimate description of this reality must be a mathematical one, as mathematics is our only language for describing objective, observer-independent relationships and structures. If a reality is to be well-defined and not just a figment of our imagination, it must have properties and relations that are independent of our human language or consciousness. Mathematics is the ultimate language of such objective structures. From here, he makes the radical leap. If the complete description of a reality is a mathematical structure, and that structure has no baggage, no undefined or human-dependent concepts, then the reality is that mathematical structure. Existence and mathematical existence are, at the deepest level, the same thing. This leads to a staggering and almost unimaginable vision of the cosmos, which Tegmark calls the Level 4 multiverse. If physical existence is equivalent to mathematical existence, then every mathematical structure that is logically self-consistent must also correspond to a physically real universe. Every possible set of equations, every possible geometry, every abstract structure that can be defined by a mathematician also describes a real, existing universe. The multiverse we have discussed, containing universes with different physical constants, would just be a tiny subset of this ultimate ensemble, containing only those mathematical structures complex enough to support observers like us. There would be other universes governed by entirely different mathematics, perhaps with different numbers of dimensions, different fundamental objects, and properties so alien that we cannot even begin to imagine them. Our universe, with its specific set of mathematical laws, quantum field theory, general relativity, is just one inhabitant of a vast, timeless, Platonic realm of all possible mathematical forms. The mindfuck of this hypothesis is its complete inversion of the usual order of things. We usually think that existence is primary, and mathematics is a tool we use to describe it. Tegmark's hypothesis suggests that the mathematical structure is primary, and our subjective experience of a physical, evolving universe is how that structure feels from the inside, from the perspective of a self-aware substructure, like a human being, within it. Our perception of time's flow, for example, might be a subjective illusion generated by our consciousness processing information within a static, four-dimensional mathematical structure, the block universe. The feeling of being in a physical world would be the way a complex algorithm, a self-aware pattern, experiences its own logical unfolding. This hypothesis offers its own unique and elegant solutions to some of the deepest questions we have been exploring. The unreasonable effectiveness of mathematics is no longer unreasonable, it is a tautology. The universe is perfectly described by math because it is math. The fine-tuning problem is also addressed. In the vast landscape of all possible mathematical structures, most will be too simple or too chaotic to support self-aware substructures, observers. Only those structures with a certain richness and complexity will contain observers. We find ourselves in a universe that appears fine-tuned for us because we could only exist in a mathematical structure with the requisite complexity. Again, it is a form of observer selection bias, but on a grand mathematical scale. The simulation hypothesis also finds a natural place within this framework. A simulated universe is, by definition, a computational and therefore mathematical structure. In the Level 4 multiverse, our universe could be a mathematical structure that is being computed or explored by another, more complex mathematical structure, the simulator's universe. The distinction between a real universe and a simulated one becomes a distinction between different types of mathematical structures and their relationships. Of course, the mathematical universe hypothesis is extremely speculative and sits on the very edge of science and metaphysics. It is profoundly difficult to test. How could we ever prove that our reality is a mathematical structure and not just described by one? What experiment could distinguish between a physical world that perfectly obeys mathematical laws and a world that is those laws? The hypothesis is also criticized for being ontologically extravagant, positing the existence of an infinite number of other universes without any direct evidence. It raises deep questions about what it means for a mathematical structure to exist. Does it need to be computed? Does it need to be thought of? Or does it exist in a timeless, Platonic sense? Despite these challenges, the hypothesis provides a powerful and logically coherent, if deeply counterintuitive, framework for thinking about the ultimate nature of reality. It is the ultimate expression of rationalism, the belief in a universe that is, at its core, a logical and intelligible structure. As you continue to fall asleep, allow your mind to gently dissolve the distinction between the physical and the mathematical. Imagine the chair you are on, the air you are breathing, your own body as not being made of stuff, but as being intricate patterns, relationships, and structures in a vast, timeless mathematical object. See the laws of physics as the axioms of this grand geometric form. Acknowledge the profound mystery and elegance of this idea. that the entire, rich, vibrant experience of your existence might be the subjective view from inside a perfect, pure, and eternal mathematical equation. Find deep relaxation in this ultimate abstraction, in the idea that you are a part of a cosmic thought, a self-aware pattern in a grand logical design, resting peacefully, floating calmly in the silent, beautiful, and profoundly ordered world of pure mathematics. The concept of emergence. We have spoken of the laws and constants that seem to govern our universe, the fundamental rules of the cosmic game. Let us now turn our attention to one of the most mysterious, powerful, and creative principles by which this game is played, the concept of emergence. This is the process by which complex systems and patterns arise out of a multiplicity of relatively simple interactions. It is the way that order, novelty, and sophisticated behavior can spontaneously appear from a state of underlying simplicity or even chaos, without a central plan or an external designer. The intricate beauty of a snowflake emerging from the simple physics of water molecules, the complex colony of an ant hill arising from the simple rule-following behavior of individual ants, the phenomenon of life itself emerging from non-living chemistry, and consciousness emerging from the firing of non-conscious neurons, these are all examples of emergence. This concept is a profound mystery that questions our intuitive, top-down understanding of creation and control. It suggests that the universal order is not just imposed from above by fixed laws, but is also constantly being built from the bottom up, through the creative interplay of countless small parts. Contemplating this self-organizing power of the universe is a pathway to deep relaxation and awe as you fall asleep. To grasp the essence of emergence, we must embrace the idea that the whole is more than the sum of its parts. A single water molecule, H2O, has a certain set of properties, but it is not wet. Wetness is an emergent property that arises only from the collective interaction of a vast number of water molecules. A single neuron is a complex biological cell, but it does not think or feel. Consciousness is an emergent property of the coordinated interaction of billions of neurons in the brain. A single ant is a simple creature operating on a limited set of instinctual rules, but an entire ant colony can exhibit incredibly complex, intelligent behavior such as building elaborate nests, farming fungi, or finding the most efficient path to a food source. The intelligence of the colony is an emergent property that resides in the network of interactions, not within any individual ant. Philosophers and scientists often distinguish between two types of emergence, which mirrors a distinction we explored earlier. Weak emergence refers to properties that are novel and surprising at a macroscopic level, but are, in principle, fully understandable and predictable from a complete knowledge of the system's components and their interactions. The intricate patterns in a flock of birds, a murmuration, are a classic example. While the flock's behavior seems holistic and coordinated, it can be simulated and explained by each individual bird following a few simple rules, like stay close to your neighbors, avoid collisions, and align with their average direction. The overall pattern is emergent, but not fundamentally mysterious or irreducible. Strong emergence, on the other hand, is a far more radical and controversial idea. It posits that some emergent properties are genuinely novel and irreducible, possessing causal powers that cannot be explained or predicted from the properties of their constituent parts, even with complete information and unlimited computational power. These properties represent a true, ontological novelty, a new layer of reality coming into being. Consciousness is the most frequently cited candidate for strong emergence. Many philosophers and scientists find it difficult to imagine how the subjective, qualitative experience of redness, or joy, could ever be fully explained or predicted solely by understanding the objective, quantitative interactions of neurons. They argue that consciousness is a fundamentally new kind of property that emerges from a certain level of biological complexity, but is not reducible to it. Life itself, the transition from inanimate chemistry to a living, self-replicating organism, is another potential example of strong emergence. If strong emergence is real, it's a profound mindfuck, suggesting that a purely reductionist view of science, the idea that everything can be explained by the physics of its smallest parts, is incomplete. It implies that the universe has a genuine creative capacity to produce new kinds of existence as complexity increases. The concept of emergence provides a powerful alternative framework for understanding the universal order, one that does not necessarily rely on a preordained grand design or the extreme fine-tuning of initial conditions. It suggests that order can arise spontaneously through self-organization. The laws of physics might provide the basic canvas and the simple rules of interaction, but the rich, complex, and ordered structures we see in the universe, from galaxies and stars to life and consciousness, are the emergent results of these rules playing out over billions of years. This perspective sees the universe as less like a static, perfectly designed clockwork, and more like a dynamic, creative, and constantly evolving ecosystem. This has profound implications for how we view our own existence. We are not just collections of atoms governed by the laws of physics. We are emergent beings. Our thoughts, our feelings, our consciousness, our very sense of self, are emergent properties of an incredibly complex biological system. This view doesn't diminish our significance. In many ways, it enhances it. It frames us as participants in the universe's ongoing creative process, a process by which complexity and awareness naturally arise from simplicity. The mystery of emergence lies in its mechanism. How does the transition from chaotic, simple interactions to coherent, large-scale order happen? Scientists study this using complexity theory, chaos theory, and network theory. They find that many emergent systems share common features like feedback loops, nonlinear dynamics, and a tendency to operate in a critical state, at the edge of chaos, a delicate balance between rigid order and pure randomness that seems to be most fertile for the emergence of novelty and complex adaptation. The precise principles governing this creative leap from micro to macro, however, are still an area of intense research and philosophical debate. Is strong emergence real, or is it just a placeholder for a deeper level of reductionist explanation we haven't yet found? As you continue to fall asleep, let your mind contemplate the creative power of emergence. Picture a single water molecule and then a vast ocean with its waves and tides and wetness. Picture a single neuron and then the vast, interconnected network of your brain, giving rise to this very conscious thought. Picture a single bird and then a breathtaking, swirling murmuration of thousands, moving as one. See how simple parts, through their interaction, can create wholes with new, surprising, and beautiful properties. Let go of the need for a single top-down designer to explain the order of the universe. Find deep relaxation in the idea of a self-organizing cosmos, a reality that is constantly creating itself from the bottom up. Appreciate your own existence as a profound emergent phenomenon, a complex harmony born from the simple laws of physics playing out over cosmic time, resting peacefully, a part of the universe's endless creative unfolding from chaos to consciousness. Self-organizing systems in nature. Having introduced the abstract concept of emergence, let us now ground this idea by exploring the beautiful, tangible examples of self-organizing systems in nature. All around us, from the microscopic to the cosmic, we see intricate patterns and complex behaviors that arise spontaneously, without a leader, a blueprint, or an external organizing force. A flock of birds, a school of fish, a colony of ants, the intricate six-fold symmetry of a snowflake, the spiral arms of a galaxy. These are all systems where local, simple interactions between individual components give rise to global, complex, and coherent order. These systems are a living testament to the principles of emergence and self-organization, providing powerful evidence for a universe that is not just governed by static laws, but is dynamically and creatively ordered from within. Contemplating these natural instances of order from chaos is a deep psychology mystery in the natural world, questioning our anthropocentric bias towards centralized control and design, and offering a profound sense of peace and relaxation as you immerse yourself in the elegant, decentralized intelligence of nature as you fall asleep. Let's begin with one of the most mesmerizing examples: a murmuration of starlings. In the evening sky, a flock of thousands of birds can move as a single fluid entity, creating breathtaking, ever-shifting three-dimensional patterns. It looks like a choreographed dance on a massive scale. Yet there is no leader, no conductor, no one giving orders. Computer models have shown that this complex, cohesive behavior can be generated if each individual bird follows a few very simple rules. 1. Stay close to your neighbors, a cohesion rule. 2. Avoid colliding with your neighbors, a separation rule. 3. Align your direction and speed with the average of your nearby neighbors, an alignment rule. From the repeated application of these simple local rules by thousands of individuals, the beautiful, unpredictable, and yet perfectly coordinated global pattern emerges. The intelligence of the flock is not in any single bird. It is a distributed, self-organizing property of the entire system. The flock thinks as one, yet is composed of many simple parts. Consider the ant colony. An individual ant is a relatively simple creature with a limited behavioral repertoire. Yet, an ant colony can achieve incredible feats of collective intelligence. They build complex, temperature-regulated nests with specialized chambers. They organize efficient foraging trails, finding the shortest path to food sources. They engage in sophisticated warfare. They even practice a form of agriculture, farming fungi. Again, there is no central command center, no queen issuing orders. This complex colony-level behavior emerges from the simple interactions of thousands of individual ants, each one responding to local chemical signals, pheromones, and simple environmental cues. This process, known as stigmergy, is where an individual's action leaves a trace in the environment that influences the subsequent actions of other individuals. An ant finding food lays down a pheromone trail. Other ants are more likely to follow stronger trails. This feedback loop quickly reinforces the most efficient path, allowing the entire colony to solve a complex optimization problem without any single ant having a map or an overview of the situation. The colony's intelligence is an emergent property of the environment and the simple rules of its agents. Let's zoom out to the cosmic scale. The beautiful, spiral arms of a galaxy are another example of a self-organizing system. These arms are not rigid structures like the spokes of a wheel, with stars permanently attached to them. Stars are constantly moving in and out of the arms. The spiral arms are density waves, regions of higher gravitational density that propagate through the galactic disk like a cosmic traffic jam. As stars and gas clouds enter this dense region, they are compressed, triggering new star formation, which is why the arms are so bright with young blue stars, and then they pass out the other side. The spiral pattern is a stable, large-scale structure that is self-perpetuating, arising from the gravitational interactions of the billions of stars within the galaxy. No external force sculpted these beautiful spirals. They are a natural, emergent form of universal order. Even a non-living thing, a snowflake, exhibits profound self-organization. The intricate and unique six-fold symmetry of every snowflake is not the result of a tiny, detailed blueprint. It emerges from the simple, local rules of how water molecules crystallize. As a snowflake falls through the clouds, it experiences ever so slight changes in temperature and humidity. These tiny changes in its local environment affect how new water molecules attach to its growing crystal lattice. Because the six arms of the snowflake experience roughly the same atmospheric journey at the same time, they grow in a similar, yet intricately detailed, way, resulting in the overall symmetry. The complex, unique beauty of the final form is an emergent record of its journey, governed by simple physical laws. The mindfuck of self-organizing systems is their profound challenge to our intuitive models of creation and control. We are top-down creatures. We design things with a blueprint, a plan, a central authority. Nature, it seems, often works differently. It creates intricate order from chaos in a bottom-up, decentralized fashion. This questions the very necessity of a designer in the grand design arguments. If such incredible complexity and order can arise spontaneously from simple local interactions, then perhaps the order we see in the universe, including the emergence of life itself, does not require an external, intelligent creator. It might be an inherent, natural property of complex systems. The mystery lies in uncovering the universal principles of self-organization. Are there common mathematical laws or principles that govern the emergence of order in flocks of birds, ant colonies, galaxies, and perhaps even in economic markets and human societies? Researchers in complexity science and systems theory are actively searching for these deeper principles. They explore concepts like feedback loops, critical points, network effects, and adaptation as the building blocks of this emergent order. Contemplating these self-organizing systems in nature can be a source of deep peace and inspiration. It shows us a model of intelligence that is distributed, collaborative, and emergent, rather than centralized and hierarchical. It reveals a universe that is not a static, passive machine, but a dynamic, creative, and constantly unfolding process. It reconnects us with the intricate, intelligent beauty of the natural world. As you continue to fall asleep, let your mind be filled with these images of emergent order. A swirling murmuration of starlings, a galaxy spinning its spiral arms, the silent, perfect growth of a snowflake. See them as a testament to the universe's innate capacity for self-organization. Acknowledge that profound complexity can arise from the simplest of rules, repeated over and over. Let go of the need for a single, central controller to explain the order you see around you. find deep relaxation in the idea of a decentralized, bottom-up intelligence woven into the fabric of existence itself, resting peacefully, feeling yourself as a part of this vast, interconnected, and beautifully self-organizing cosmos. The nature of complexity itself. We have spoken of the universe as a place of profound order and intricate structure. We have marveled at the emergence of elaborate systems from simple rules. Let us now turn our attention to the very quality that these systems embody, the nature of complexity itself. What do we mean when we say something is complex? Is it simply a matter of having many parts? Or is there a deeper, more specific quality to the kind of organized complexity we see in a living cell, a brain, an ecosystem, or a human society? The attempt to define and measure complexity is a profound scientific and philosophical challenge, a mystery that lies at the heart of our quest to understand the universe. It questions the very line between the simple and the intricate, the random and the ordered. Contemplating the nature of this elusive property can be a pathway to deep relaxation, allowing us to appreciate the rich, multi-layered texture of our existence as you fall asleep. At first glance, we might think of complexity as the opposite of simplicity. A single hydrogen atom is simple, a human brain is complex. A straight line is simple, the coastline of Norway is complex. But this intuitive idea is not enough. A container of gas, for instance, contains a colossal number of interacting particles, yet we would describe its overall state with a few simple variables, like temperature and pressure. It is complicated, but not necessarily complex in the way a living organism is. Similarly, a perfectly ordered crystal lattice is highly structured, but also simple in its repetitive pattern. A purely random sequence of letters is maximally disordered and unpredictable, but it lacks the structure and meaning we associate with complexity. This suggests that true organized complexity exists in a delicate and mysterious space between perfect order and pure randomness. It is a sweet spot, a state of being that is rich in structure and information, but not rigidly predictable. It is patterned but not simply repetitive. A crystal is ordered, a gas is random, but a living cell is complex. The sequence of letters in a great novel is complex. It is not a repeating pattern, nor is it random gibberish. It has a deep, hierarchical structure. This idea of complexity at the edge of chaos is a central theme in the modern sciences of complexity. So, how do scientists and philosophers try to formalize this intuition? There are several approaches. One is algorithmic complexity, or Kolmogorov complexity. This defines the complexity of an object or a piece of information as the length of the shortest possible computer program required to describe or generate it. A highly repetitive string like a bababab has very low algorithmic complexity because you can describe it with a very short program, print AB forever. A purely random string has very high algorithmic complexity because there is no shorter way to describe it than to simply write out the entire string itself. A truly complex object, like a human genome, has a description that is very long, but also contains deep, nested patterns and redundancies. It is compressible but not simple. This definition captures the idea of structure and information content, but it has a major drawback. It is generally impossible to prove that you have found the shortest possible program, making it a theoretically powerful but often impractical measure. Another approach focuses on effective complexity or logical depth. This is the idea that the complexity of a system is related to the amount of computational effort required to build it up from its simplest components. A simple gas is easy to build. A living organism is the result of billions of years of complex evolutionary computation. The history and the process of formation are part of its complexity. This connects complexity to time and the emergence of order. The universe itself can be seen as a system that is growing in effective complexity, as simple initial states have evolved over billions of years into the rich, structured cosmos we see today. The mystery of complexity lies in its origin. If the second law of thermodynamics dictates that the universe as a whole tends towards increasing disorder or entropy, how can we explain the local emergence of such incredible pockets of order and complexity, like life, brains, and human civilization? This is a deep paradox. The standard answer is that the second law applies only to closed systems. The Earth is not a closed system. It receives a constant influx of low-entropy energy from the Sun. This energy flux allows life to build local order and complexity, while still increasing the total entropy of the universe as a whole, by radiating waste heat, a more disordered form of energy, back into space. Life, in this view, is a remarkable process that surfs the wave of cosmic entropy, creating temporary local islands of complexity in a universe that is overall winding down. Life doesn't violate the second law, it is a beautiful and intricate consequence of it. This mindfuck of complexity is the realization that the most ordered and sophisticated structures in the universe, including ourselves, are in a sense the most improbable. We are the statistical flukes, the beautiful anomalies that have temporarily fought off the cosmic tide of disorder. Our existence is a testament to the universe's capacity to generate profound order from chaos, to build intricate machinery from simple parts. It questions any simplistic view of the universe as merely a system running down. It is also a system that is, in pockets, running up, building structures of ever-increasing complexity. Contemplating the nature of complexity itself can evoke a profound sense of awe. It allows us to see the world not as a collection of static objects, but as a nested hierarchy of systems, each with its own emergent properties and level of organization. It connects the patterns in a snowflake, the structure of a language, the workings of an economy, and the evolution of life under a single unifying, though still mysterious, conceptual umbrella. It reframes the universe as a complexity-generating machine. As you continue to fall asleep, allow your mind to hold the concept of complexity. See it not as mere complication, but as the rich, structured space between perfect, sterile order and pure, meaningless randomness. Picture the beautiful, intricate structure of a living cell, a marvel of self-organizing complexity. Contemplate the profound mystery of how such order can arise in a universe that tends towards decay. Find deep relaxation in the idea that you, yourself, are one of the most complex phenomena in the known universe, an island of intricate order, a product of billions of years of cosmic and biological evolution. Resting peacefully, a part of the universe's profound and ongoing journey from simplicity to complexity. The Gaia hypothesis: is Earth a single organism? Having contemplated the emergence of complexity and order, let us now focus our lens on the most complex system we know, our own planet Earth. We typically think of Earth as a giant rock, a physical stage upon which the drama of life unfolds. We see life as a collection of individual, competing organisms living on the planet. But what if this view is incomplete? What if the planet and the totality of life upon it, the biosphere, function as a single, integrated, self-regulating system? This is the core of the Gaia hypothesis, a radical, beautiful, and controversial idea proposed by scientist James Lovelock and microbiologist Lynn Margulis. It suggests that we should view the Earth itself, including its oceans, its atmosphere, and all of its living inhabitants, as a vast, single living organism or superorganism. This entity, named Gaia after the Greek goddess of the earth, actively maintains the conditions necessary for its own survival. This is a profound mindfuck that questions the very distinction between life and non-life, between organism and environment, suggesting that the universal order we experience on our planet is not a passive backdrop, but an active, self-created system. Contemplating this holistic vision can be a source of deep connection and relaxation as you fall asleep. The Gaia hypothesis was born from Lovelock's work for NASA in the 1960s, searching for ways to detect life on other planets. He realized that a planet with life would look profoundly different from a dead one. A lifeless planet would be in chemical equilibrium, its atmosphere dictated by simple physics and chemistry. Earth, however, is in a state of wild chemical disequilibrium. Our atmosphere, with its high concentration of oxygen and methane, is a highly unstable and reactive mixture that should not exist according to pure chemistry. It is like a carefully maintained fire. What maintains this fire? Life itself. The oxygen is a waste product of photosynthesis by plants and algae. The methane is produced by microbes. The composition of our atmosphere is a product of biological activity. Lovelock and Margulis identified numerous such feedback loops. The salinity of the oceans has remained remarkably stable for billions of years at a level optimal for most life, despite the constant dumping of salts by rivers. They proposed that biological processes, like the formation of salt flats by microbes, might regulate this. The Earth's average surface temperature has also remained within a relatively narrow life-permitting range for billions of years, despite the sun's output having increased by as much as 30%. The Gaia hypothesis suggests that life itself has acted as a global thermostat, regulating the climate. For example, plankton in the oceans can release a chemical that promotes cloud formation. More clouds reflect more sunlight back into space, cooling the planet. This could be part of a negative feedback loop. If the planet gets too warm, the plankton might thrive, produce more clouds, and cool it back down. In its strongest form, the hypothesis suggests that these regulatory systems are not just accidental byproducts, but are part of a goal-directed or teleological system that acts to preserve life. Gaia, in this view, is a living superorganism with a kind of planetary-scale physiology, actively maintaining its own homeostasis. This is the version of the hypothesis that has been most controversial and has been criticized by many mainstream evolutionary biologists. They argue that natural selection operates on individual organisms, not on a global superorganism. There is no plausible mechanism by which life as a whole could evolve to regulate the planet for its own benefit. Such global cooperation cannot be explained by the selfish gene perspective of neo-Darwinism. In response to this criticism, a more moderate version, often called Gaia theory, has emerged. This version reframes the idea in terms of complex systems science and coevolution. It doesn't claim that Gaia is a conscious or purposeful being, but that the Earth's systems, the biosphere, atmosphere, oceans, etc., are so tightly coupled that they create complex feedback loops that have, as an emergent property, a tendency towards self-regulation. Life profoundly affects the environment, and the environment, in turn, profoundly affects the evolution of life. Over billions of years, this coevolutionary dance has created the stable, resilient, and interconnected Earth system we see today. The stability is an emergent property of the complex adaptive system, not a sign of conscious intent. This weaker version is more widely accepted and has become a cornerstone of modern Earth system science. The mindfuck of the Gaia hypothesis, even in its weaker form, is its radical challenge to our sense of separation from nature. We tend to see ourselves as living on the Earth. The hypothesis suggests we are a part of the Earth, in the same way that a single cell is a part of our body. We are a component of a much larger, interconnected system. Our actions, like the release of carbon dioxide, are not just affecting the environment, they are altering the physiology of the superorganism we are part of. This questions our anthropocentric worldview and our illusion of being masters of nature, reframing us as components within a vast, complex, and deeply interconnected living system. The mystery lies in the nature of this planetary scale regulation. How sensitive are these feedback loops? How resilient is the Gaian system to major perturbations, like the one humanity is currently inflicting? Is consciousness itself, which has emerged from this system, now the part of Gaia that has become self-aware, capable of consciously influencing the planet's future? These are deep and urgent questions that the Gaian perspective forces us to confront. Contemplating the Gaia hypothesis can foster a profound sense of connection and ecological responsibility. It transforms our view of the planet from a dead rock with a thin veneer of life to a single, vibrant, and integrated entity. It makes the air we breathe feel like the breath of a larger being, the oceans like its circulation, the forests like its lungs. It gives a deep, almost spiritual, meaning to the interconnectedness of all living things. As you continue to fall asleep, imagine your own breath, in and out. Now, imagine the breath of the world's forests inhaling carbon dioxide and exhaling oxygen. Feel your own small biological process as a tiny part of this vast planetary respiration. Contemplate the Earth not as a place but as a single living, breathing being, Gaia. See the clouds, the oceans, the forests, the myriad of creatures, including yourself, as organs and cells of this vast superorganism. Let go of the feeling of being a separate, isolated individual, and find deep relaxation in the feeling of being a part of something immeasurably ancient, complex, and alive, resting peacefully, held safely within the vast, self-regulating, and deeply mysterious embrace of our living planet. The role of chance versus necessity in the cosmos. Throughout our cosmic contemplation tonight, we have repeatedly encountered a deep and fundamental tension, a philosophical fault line that runs beneath almost every major question about the universal order. This is the tension between chance versus necessity. Is the universe the way it is because it had to be, its properties dictated by some deep, unchanging, and logically inevitable principle? Or is it the way it is because of a series of cosmic accidents, a cascade of random events and frozen contingencies, a lucky roll of the cosmic dice? Is the order we see around us a manifestation of an underlying necessity, or is it merely the fleeting, improbable pattern that has emerged from a deep, underlying chaos? This debate is a profound mystery, questioning whether our existence is a meaningful inevitability or a meaningless fluke. It is a mindfuck that forces us to confront the ultimate nature of causality and explanation, inviting deep relaxation through the calm acceptance of the profound ambiguity that lies at the heart of reality as you fall asleep. Let's first explore the idea of necessity. This is the viewpoint of a universe governed by an ironclad logic, a reality where things are the way they are because they could not possibly be any other way. In its strongest form, this perspective suggests that a theory of everything could one day be discovered that would not only unify the forces of nature but would also demonstrate that the fundamental constants, the number of dimensions, and the very laws of physics themselves are all uniquely determined by mathematical consistency. There would be no free parameters, no dials that could be tweaked. The universe would be a single, perfect, logical solution. From this viewpoint, the fine-tuning of the universe for life is not a coincidence to be explained by anthropic principles or multiverses. It is a direct consequence of this underlying necessity. Life would be, in a sense, written into the very fabric of logic itself. This is a universe of profound, inherent order, where chance is merely an illusion of our incomplete knowledge. Every event, from the Big Bang to this present moment, would be the unfolding of a necessary, inevitable sequence. This is a deeply deterministic and, for some, a deeply comforting vision of the cosmos, one imbued with a sense of ultimate rationality and coherence. Now, let us turn to the other side, the universe of chance. This perspective suggests that the fundamental properties of our universe are not necessary, but are the result of random, contingent events. The laws of physics might not be unique. The values of the fundamental constants might be the result of a random symmetry-breaking event in the early universe. This is the view that is implicitly supported by the multiverse hypothesis. In a multiverse, the laws and constants are different in different universes because they are the result of a random cosmic lottery. Our universe has the properties it does not because of necessity, but because of the sheer luck of the draw, combined with the observer selection bias that we can only exist in one of the lucky, life-permitting universes. In this view, chance is not just an illusion of ignorance, but a fundamental feature of reality. The probabilistic nature of quantum mechanics is often seen as the ultimate bedrock of this cosmic randomness. The decay of a radioactive atom, the position of a particle, the outcome of a quantum measurement, these events are, according to the standard interpretation, genuinely random, not predetermined by hidden variables. If the universe at its most fundamental level is governed by chance, then perhaps its large-scale properties are also the result of a grand cosmic game of probability. Our existence in this picture is not a necessary outcome, but a fantastically improbable accident, a lucky fluctuation in a vast, indifferent, and fundamentally random cosmos. This is a vision that can be seen as either terrifyingly meaningless or beautifully liberating, a universe where nothing is guaranteed, and our brief, improbable existence is all the more precious for it. The mindfuck of the chance versus necessity debate is that both perspectives have a powerful allure, and we seem to have no definitive way to choose between them. We are trapped inside the one universe we can observe, trying to deduce whether its rules are the only possible rules, or just the rules of this particular game. Science seems to offer evidence for both sides. The elegant symmetries and mathematical consistency of our physical laws seem to hint at a deep, underlying necessity. Yet, the apparent randomness of quantum events and the profound fine-tuning required for our existence seem to point towards an essential role for chance and selection. This mystery permeates every level of our understanding. Is the evolution of life on Earth a story of inevitable progress towards complexity and intelligence, a necessary outcome of the laws of biology? Or is it a tale of radical contingency, a series of lucky accidents and catastrophic extinction events that could have easily turned out differently? Paleontologist Stephen Jay Gould famously argued that if you were to replay the tape of life, the chances of humanity appearing again would be virtually zero, championing the role of chance. Others see convergent evolution, the independent evolution of similar traits like eyes or wings, as evidence for a degree of necessity in the pathways of life. This profound question also shapes our personal, philosophical outlook. Do we live in a universe with an inherent, necessary order and purpose that we can discover and align ourselves with? Or do we live in a fundamentally random universe where we must create our own meaning and purpose in the face of cosmic indifference? This is the core tension between many classical religious and philosophical systems and more modern existentialist viewpoints. The debate is not just academic, it reflects a deep psychological duality. The human mind craves both structure and freedom, both predictability and novelty. The idea of a necessary, ordered universe provides a sense of safety, meaning, and coherence. The idea of a chance-filled, open universe provides a sense of possibility, freedom, and the thrill of the unknown. Perhaps the reality of our cosmos involves a deep and paradoxical interplay of both. Perhaps there are necessary laws, but the outcomes of those laws are probabilistic and contingent. Perhaps the framework is necessary, but the story that unfolds within it is a product of chance. As you continue to fall asleep, allow your mind to hold these two powerful, competing visions of the cosmos. On one hand, a universe of perfect necessity, a single, elegant crystal of logic, where your existence is an inevitable and meaningful note in a grand symphony. On the other hand, a universe of boundless chance, a cosmic lottery where your existence is a fantastically improbable and precious winning ticket. Let go of the need to choose between them. Acknowledge that the true nature of the universal order may be a profound blend of both, or something else entirely. Find deep relaxation in the acceptance of this fundamental ambiguity. The mystery of whether the universe is a given or a throw of the dice is perhaps the ultimate question. Resting peacefully, floating calmly in a reality that is at once deeply ordered and profoundly unpredictable. Philosophical arguments for a designer, teleological arguments. Having contemplated the intricate order, the apparent fine-tuning, and the elegant symmetries of the cosmos, it is only natural that we now turn to one of the most ancient, intuitive, and enduring explanations for this perceived design. We will gently explore the philosophical arguments for a designer, often known as teleological arguments or arguments from design. From the intricate complexity of a biological organism to the vast, law-like regularity of the heavens, the universe often seems to exhibit the hallmarks of purpose, intention, and craftsmanship. The teleological argument, in its many forms, takes this perception of design as evidence for the existence of a cosmic designer, a purposeful intelligence responsible for the universal order. While these arguments have been subject to intense philosophical and scientific criticism, they remain powerful and emotionally resonant, tapping into a deep human intuition that complex, functional order does not arise from mere chance. This is a profound mystery that questions the very origin of the cosmos, suggesting that our existence might be the product of a deliberate, creative act. Let us calmly and respectfully explore the logic of this ancient line of thought as you fall asleep. The classic and most famous formulation of the argument comes from the 18th century theologian William Paley and his watchmaker analogy. Paley asks us to imagine walking on a heath and stumbling upon a stone. We might easily conclude the stone has lain there forever, a simple product of natural forces. But what if we were to find a watch? We would observe its intricate mechanism, the way its gears and springs are perfectly arranged to perform a specific function, telling time. We would never conclude that this complex, purposeful object had simply appeared by chance. The intricate design and clear purpose of the watch would force us to infer the existence of a watchmaker, an intelligent designer who crafted it with a specific end in view. Paley then extends this analogy to the natural world. Look at the human eye, he argues, with its incredibly complex and coordinated parts. The lens, the iris, the retina, all working together for the clear purpose of vision. Is this not far more complex and wonderful than a watch? Therefore, just as the watch implies a watchmaker, the intricate design of the natural world, from the eye to the solar system, implies a divine, intelligent designer. This form of the argument is an argument from analogy. It relies on the perceived similarity between human-made objects and natural systems. It is powerful because it taps into our direct experience. In our world, complex, functional systems are always the product of intelligent design. A more modern version of this argument focuses not on biological complexity, but on the fine-tuning of the physical constants of the universe, which we have already explored. The fact that the universe seems to be balanced on a knife's edge for life to exist is seen by proponents as powerful evidence for a grand design. The argument here is probabilistic. The odds of all these constants falling into the life-permitting range by pure chance are so astronomically small that it is far more reasonable to infer that they were deliberately set or tuned by a cosmic intelligence. This is like finding a lottery machine that has been rigged to produce a specific winning number. The improbability of the outcome points towards an intelligent agent behind the scenes. This fine-tuning argument is currently one of the most active and debated teleological arguments in philosophy and cosmology. These arguments are not intended as scientific theories, but as philosophical inferences to the best explanation. They claim that the hypothesis of a designer provides a more rational, more satisfying, and less improbable explanation for the observed order of the universe than the alternative of pure, unguided chance. They appeal to our intuition that order and purpose are signs of a mind. However, the teleological arguments have faced powerful criticisms throughout history, and these criticisms are crucial for understanding the depth of the philosophical debate. The most famous critic of the classic design argument was the philosopher David Hume. Hume pointed out that the analogy between a human-made object like a watch and the entire universe is weak. The universe is a unique, singular entity. We have no experience of other universes being created to know if ours is typical or if its order requires a designer. Furthermore, he argued, even if we were to infer a designer, the argument tells us nothing about the nature of that designer. It doesn't prove the existence of a single, all-powerful, all-good God of classical theism. The universe has flaws and imperfections, the problem of evil, which we'll explore next, which might suggest a designer who is clumsy, malevolent, or perhaps a committee of designers. The analogy, Hume argued, is too weak to support the strong conclusions of traditional religion. The most powerful scientific challenge to the biological design argument came from Charles Darwin's theory of evolution by natural selection. Darwin provided a powerful, purely naturalistic mechanism for explaining the appearance of design in living organisms without invoking a designer. The intricate complexity of the eye, for example, could be explained as the result of a long, gradual process of random variation and natural selection, where traits that conferred a slight survival advantage were passed on and accumulated over millions of years. Evolution is a blind watchmaker. It produces complex, functional systems automatically, without any foresight or purpose. For many, Darwin's theory completely dismantled the biological version of the argument from design. The modern fine-tuning argument is not refuted by Darwin, as it applies to the fundamental laws of physics that allow for evolution to occur in the first place. However, it is challenged by the multiverse hypothesis, as we've seen. The multiverse provides a naturalistic alternative for explaining the fine-tuning, replacing a single designer with a vast ensemble of universes and an observer selection bias. The mindfuck of the teleological argument is its enduring power despite these powerful critiques. The intuition that the profound order and complexity of the cosmos is a sign of a mind is incredibly strong and persistent. It questions whether purely naturalistic explanations like chance and selection can ever fully account for the feeling of wonder and purpose that the universe seems to evoke. It keeps the door open to a reality that is not just physical, but also mental or intentional at its deepest level. As you continue to fall asleep, allow your mind to hold the two perspectives in gentle balance. On one hand, the vision of a self-organizing universe, where order emerges from the blind, impersonal workings of chance and natural law. On the other hand, the vision of a designed universe, a grand design, where the intricate order and beauty you see are the handiwork of a cosmic intelligence. Acknowledge the power of the watchmaker analogy, the deep intuition that such complexity cannot be an accident. Also acknowledge the power of the critiques, the alternative explanations of evolution and the multiverse. Find deep relaxation in the mystery itself. The question of design is perhaps unanswerable by science alone. It is a philosophical choice, a matter of how we choose to interpret the profound and beautiful order of our existence, resting peacefully, floating calmly in a universe that is either a masterpiece of chance or a masterpiece of art. Philosophical arguments against the designer, problem of evil. Having just explored the powerful and intuitive arguments for a cosmic designer, drawn from the evidence of order and fine-tuning, we must now, in the spirit of balanced contemplation, turn to the most profound, emotionally wrenching, and historically powerful argument against the existence of such a being, at least as traditionally conceived. We return to the problem of evil, which we have touched upon in other contexts, but let us now focus on it as a direct philosophical rebuttal to the idea of a grand design. The teleological argument asks us to look at the goodness of the design, its complexity, its order, its fitness for life. The problem of evil asks us to look at its flaws, the immense and seemingly gratuitous suffering, the cruelty, the chaos, the waste. If the universe is the creation of a designer, particularly one who is said to be all-powerful, all-knowing, and all-good, then the existence of evil, pain, and suffering in that universe presents a profound and perhaps insurmountable paradox. This is not just an intellectual puzzle. It is a deep, existential, and emotional challenge that questions the very goodness and coherence of any supposed universal order. It is a mindfuck that forces us to confront the darkest aspects of existence and ask how they can possibly be reconciled with the idea of a benevolent creator. The argument, in its logical form, is stark and powerful. It is often presented as an inconsistent triad of propositions. An omnipotent, omniscient, and omnibenevolent God exists. Evil exists. These two statements are logically incompatible. If God is all good, omnibenevolent, He would want to eliminate all evil and suffering. If God is all-powerful, omnipotent, He would be able to eliminate all evil and suffering. And if God is all-knowing, omniscient, He would know about all evil and suffering and how to prevent it. Therefore, if such a God existed, evil and suffering should not exist. But evil and suffering clearly do exist, in horrific abundance. From the agony of a child dying from a painful disease, to the immense cruelty of war and genocide, to the sheer destructive terror of a natural disaster like a tsunami or an earthquake, the world is filled with suffering that seems to serve no good purpose. The logical conclusion the argument posits is that a being with all three of these properties cannot exist. At least one of the premises, God's goodness, God's power, or God's existence, must be false. This is the logical problem of evil. But there is also the evidential problem of evil, which many find even more compelling. This version doesn't claim a strict logical contradiction, but argues that the sheer amount, type, and distribution of evil and suffering in the world provides overwhelming evidence against the existence of a good and powerful designer. It's not just that evil exists, but that there is so much of it that seems utterly pointless and gratuitous. What possible greater good, or soul-making purpose is served by a fawn being horribly burned in a forest fire, or by the immense suffering of animal predation over millions of years of evolution, or by the suffering of those with profound mental disabilities who cannot learn from their pain? The evidential argument claims that while we might be able to imagine reasons for some suffering, the vast, seemingly pointless ocean of suffering we observe makes the existence of a benevolent designer incredibly improbable. The design, if it is a design, seems deeply flawed, inefficient, and often cruel. As we noted in a previous exploration, theologians and philosophers have developed various responses, or theodicies, to try and resolve this profound challenge. The free will defense argues that moral evil is a necessary consequence of God granting humans genuine freedom, which is a greater good. But this struggles to explain natural evil, the suffering caused by diseases, disasters, and the fundamental workings of nature. Was it necessary to design a world with cancer, parasites, and tectonic plates that cause earthquakes? The soul-making theodicy argues that suffering is necessary for our moral and spiritual development, that adversity builds character. But again, this is challenged by the sheer extremity and unequal distribution of suffering. Does the unimaginable pain endured by so many truly seem like a well-designed character-building program? For many, the means seem grotesquely disproportionate to the proposed end. Other responses appeal to skeptical theism, the idea that we are simply not in a cognitive position to understand God's reasons for allowing suffering. A finite mind cannot possibly comprehend the plans of an infinite one. What appears pointless to us might be a crucial part of a universal order and grand design that is beyond our ken. While this response may be logically coherent, it often feels deeply unsatisfying on an emotional and existential level. It asks us to accept suffering on the basis of a faith in inscrutable reasons, which can feel like an evasion of the problem's moral force. The mindfuck of the problem of evil is its power to turn the argument from design completely on its head. The very same universe that one person sees as evidence of a brilliant and benevolent designer, another person can see as evidence of a clumsy, indifferent, or even malevolent one. The order and complexity of the eye is met with the flawed design of the blind spot and its susceptibility to disease. The beauty of nature is met with the brutal reality of the predator and its prey. The argument reveals that looking for design in the universe is a profoundly ambiguous task, and our conclusions are often shaped by which evidence we choose to focus on, the order and beauty, or the chaos and suffering. This questions everything about our ability to infer the nature of a creator from the creation. The existence of evil is the single greatest challenge to traditional theism and the most powerful argument for atheism or agnosticism. It forces believers to grapple with the difficult nature of faith in the face of suffering, and it provides skeptics with a powerful reason to doubt the existence of a good and loving God. As you continue to fall asleep, allow your mind to hold this profound and difficult tension. Acknowledge the incredible order and beauty in the universe, the cosmic coincidences that allow for your existence. but also, with compassion, acknowledge the immense reality of suffering and pain. Do not try to solve this ancient problem. Do not try to justify the pain or explain it away. Simply allow the paradox to be present. The deep mystery of a world that contains both breathtaking beauty and unbearable suffering. Find deep relaxation not in a comforting answer, but in the honest and courageous act of facing this difficult truth. Cultivate a sense of deep compassion for all beings who suffer within this mysterious existence, resting peacefully, holding the light and the dark together, in the profound, unresolved silence of the cosmos. The simulation hypothesis as a design theory. Having wrestled with the profound challenges of the problem of evil and the classic arguments for a divine designer, let us now turn to a modern, technologically inspired framework that reframes the entire debate. This is the simulation hypothesis, which we have explored in other contexts, but let us now consider it specifically as a form of design theory. As we've seen, this hypothesis posits that our reality is an artificial construction, a high-fidelity simulation created by a vastly superior intelligence. When viewed as a potential explanation for the universal order, the simulation hypothesis acts as a powerful, alternative form of design argument, one that shares many features with traditional theism but radically departs from it in crucial ways. It provides a potential mechanism for the fine-tuning of the universe and the existence of seemingly designed structures, but it does so in a way that is conceptually naturalistic, even while being metaphysically staggering. This is a profound mindfuck that questions the very distinction between the natural and the artificial, the creator and the programmer, God and the simulator. Contemplating our existence as a potential grand design of a different kind can be a source of deep, speculative relaxation as you fall asleep. Let's begin by seeing how the simulation hypothesis directly addresses the core tenets of the teleological argument. The classic argument from design, as we saw with Paley's watchmaker, infers a designer from the presence of complex, functional order in the universe. The simulation hypothesis takes this and provides a concrete, modern analog. The universe appears designed because it was designed. The laws of physics are not mysterious, transcendent principles, but are the source code, or the physics engine programmed by the simulators. The fine-tuning of the physical constants is not an improbable cosmic accident, but the result of the simulators carefully setting the parameters of their simulation to ensure it would be stable and capable of generating the complexity they wish to study or create. The intricate complexity of life is not a miracle, but a natural, emergent outcome of running this well-designed code over billions of years of simulated time. In this framework, the universe is a masterpiece of information technology, and the designer is a cosmic programmer or team of programmers. This perspective offers several seeming advantages over classical design arguments. Firstly, it sidesteps the need to posit a supernatural, non-physical creator. The simulators, while godlike in their power relative to us, are presumed to be natural beings existing in their own, more fundamental base reality, governed by their own set of physical laws. The act of creation is not a supernatural miracle, but an act of advanced technology. This makes the concept of a designer more palatable to a modern, scientific mindset. The grand design is not metaphysical but computational. Secondly, it provides a different lens through which to view the problem of evil. A traditional, all-good, all-powerful God who creates a universe with immense suffering is a profound theological paradox. However, if the simulators are not all good but are, for example, cosmic researchers, then the existence of suffering in our simulation might be more easily explained. The suffering might be a necessary and regrettable but ethically acceptable, to them, byproduct of a simulation designed to study the evolution of life, consciousness, or civilization in a realistic environment. A realistic ancestor simulation would, by definition, have to include the famines, the diseases, the wars, and the natural disasters that were part of that history. Or, in a more unsettling scenario, if our universe is a form of entertainment for the simulators, the suffering and conflict might be intentional features, part of the drama that makes the simulation interesting to its audience. The hypothesis allows for a creator who is morally ambiguous, indifferent, or even has motives that are completely alien to our ethical framework, thus solving the problem of evil by jettisoning the assumption of a perfectly benevolent designer. The mindfuck of the simulation hypothesis as a design theory is its radical recontextualization of our entire existence. It fulfills our deep intuition that the universe is ordered and purposeful, but the purpose might not be for our ultimate benefit. We move from being the cherished creations of a loving God to potentially being the research subjects, or even the entertainment, of a vastly superior intelligence. It questions the very meaning of our lives. Is our purpose our own to create, or is it to fulfill some function in the simulator's experiment? Are our profoundest spiritual experiences genuine connections to a transcendent reality, or are they interactions with the simulation's code, perhaps even the simulators themselves reaching into the program? A religious text could be a README file, a miracle could be a patch or a debug command. This perspective also has a fascinating relationship with the multiverse. In a way, it combines the idea of design with the idea of multiple universes. A single post-human civilization in a base reality could potentially run billions of different simulations, tweaking the laws of physics or the initial conditions in each one. This would create a kind of artificial multiverse. We would be living in one designed bubble universe, among many, but the ensemble of universes would not be the result of random chance, but of systematic exploration by an intelligent creator. This synthesizes the two leading explanations for fine-tuning into a single, albeit highly speculative, framework. Of course, the simulation hypothesis as a design theory is not without its own profound philosophical problems. As we've explored, it faces the challenge of infinite regress. If our designers are natural beings in their own reality, what explains the fine-tuning of their universe? Are they too in a simulation? This simply pushes the ultimate question of design back a level, potentially infinitely. It also faces the objection from Occam's razor. Is it truly simpler to posit an entire unseen reality and its unknown inhabitants to explain our own, rather than working with the reality we have? Furthermore, it raises deep questions about the nature of consciousness. For the simulation argument to work in a way that explains our existence, it must assume that consciousness itself is simulatable. This is a huge and proven assumption. If consciousness is a unique property of biological matter, then we could not be sims, and the fine-tuning of the universe would still require a different explanation. As you continue to fall asleep, let your mind hold the idea of the universe as a work of profound, intricate design. But see the designer not as a supernatural deity, but as a cosmic programmer and architect of a simulated reality. Contemplate the possibility that the laws of physics are its code, the fine-tuning is its parameter settings, and your own consciousness is its most complex emergent property. Does this view make the universe feel more or less meaningful? More or less real? Let go of the need for a definitive answer. Find deep relaxation in the sheer imaginative power of this modern creation myth, a story that bridges the gap between science and religion, design and naturalism. Resting peacefully within the profound, unsettling, and endlessly fascinating possibility that you are living inside a grand design of a completely different kind. The nature of order and entropy. In our quest to understand the universal order and the cosmic coincidences that allow for our existence, we must now turn to one of the most fundamental, powerful, and mysterious laws in all of physics. This is the second law of thermodynamics and its central concept, entropy. The second law, in its simplest formulation, states that the total entropy of an isolated system can never decrease over time. It can only stay the same or increase. Entropy is often described as a measure of disorder, randomness, or chaos. This law, therefore, seems to describe a universe with a built-in one-way street, a relentless tendency to move from states of order toward states of ever-increasing disorder. It is the law that explains why a hot cup of coffee always cools down, why a broken egg never spontaneously reassembles, why a neat room left to its own devices will tend towards messiness. It is the physical basis for the arrow of time. Yet this raises a profound paradox. If the universe as a whole is governed by a law of increasing disorder, how can we explain the incredible pockets of complex order we see all around us, the intricate structure of a galaxy, the exquisite complexity of a living organism, the vast information content of a human brain? This is the mystery of order versus entropy, a mindfuck that questions the very nature of creativity and complexity in a universe that seems destined for decay. Contemplating this cosmic tension is a pathway to deep relaxation as you fall asleep. Let's begin by understanding entropy more deeply. The concept is not just about messiness in a visual sense. It is a precise statistical idea. A state of high entropy is a state of high probability. There are vastly more ways for the molecules in a room to be randomly distributed, a high-entropy, disordered state, than for them to be all neatly arranged in one corner, a low-entropy, ordered state. A broken egg with its yolk and white mixed together is a high-entropy state because there are countless ways the molecules can be mixed up. A whole, unbroken egg is a low-entropy state because there are far fewer ways for its molecules to be arranged in that specific, highly structured configuration. The second law of thermodynamics is, at its core, a statement of overwhelming statistical probability. Systems, left to their own random interactions, will naturally tend to drift into their most probable, most disordered states. The universal order, from this perspective, seems to be in a constant, losing battle against the statistical certainty of chaos. This is what makes the existence of complex structures so mysterious. Life itself is the ultimate anti-entropic phenomenon. A living organism like you is a marvel of intricate, low-entropy order. You take in disordered, high-entropy energy from your environment, food, and use it to build and maintain your own highly structured, complex form, a state of incredible improbability. How does life achieve this apparent violation of the second law? The key is that the second law applies only to isolated or closed systems. The Earth and the life upon it is not a closed system. We are constantly bathed in a flood of low-entropy, high-grade energy from the sun. Life is a process that has learned to capture this incoming solar energy and use it to power the creation of local, temporary pockets of order. We build our complex bodies, our cities, our civilizations by paying for this local decrease in entropy with an even greater increase in the total entropy of the universe as a whole. We do this by radiating low-grade, high-entropy energy, waste heat, back out into the coldness of space. So, life does not violate the second law, it is a beautiful and intricate consequence of it. It is a process that skillfully surfs the cosmic energy gradient, creating stunning islands of temporary order in a universe that is overall moving towards a state of maximum entropy or heat death. The mindfuck of this realization is profound. It means that the order and complexity that define our existence are not stable, permanent states. They are fragile, temporary, and thermodynamically expensive achievements. We are improbable structures, fighting a constant, losing battle against the overwhelming statistical tide of disorder. Every act of living, thinking, and creating is an act of holding back the chaos, of temporarily reversing the cosmic trend, all powered by the energy of a distant star. It questions any notion of a static, permanent reality, reframing existence as a dynamic, energy-consuming process of maintaining order against a backdrop of decay. This leads to one of the deepest mysteries in all of cosmology, a question we have touched upon before but which now comes into sharp focus: the mystery of the universe's initial condition. If the universe naturally tends towards high entropy, why did it begin in a state of incredibly low entropy? The Big Bang, the initial state of our observable universe, must have been a state of unimaginable order and simplicity. This highly improbable low-entropy starting point is the ultimate source of all the order and complexity we see today. It is the wound-up spring that has been unwinding for 13.8 billion years, allowing for the formation of stars, planets, and life. But why did the universe start this way? Why wasn't it born into a state of maximum entropy, a chaotic, featureless soup? This is the past hypothesis, and it is a profound cosmic coincidence for which we have no definitive explanation. Is it a clue to a grand design? A feature of a pre-Big Bang reality? A consequence of the process that creates universes in a multiverse? It remains a fundamental, unanswered question. As you continue to fall asleep, become aware of the gentle, ordered rhythm of your own breath, a process that requires energy to maintain. Contemplate the incredible, improbable order of your own living body, a complex island of low entropy in a vast cosmic sea. Acknowledge the deep law of the universe that all things tend towards disorder, that this order is temporary and precious. Let this thought not be a source of anxiety, but of profound appreciation for this present moment of ordered existence. Find deep relaxation in the image of your life as a beautiful, temporary eddy in the great forward-flowing river of cosmic time and increasing entropy, resting peacefully, a fragile, beautiful, and highly improbable pattern of order, held for a moment against the vast, silent backdrop of cosmic chaos. Why did the universe start in a low-entropy state? We have just contemplated the profound law of entropy, the relentless march of the universe towards disorder, and how the complex order of our existence is a temporary island in this cosmic tide. This leads us now to what is arguably the deepest, most fundamental mystery in all of cosmology, the ultimate why question about the structure of time and reality. We have seen that the second law of thermodynamics explains the arrow of time, the reason why the past is different from the future. But the second law itself only works because of a single, colossal, and completely unexplained fact about our universe. It began in an incredibly special, highly ordered, and statistically miraculous state of very low entropy. This initial condition, often called the past hypothesis, is the ultimate source of all the order, all the complexity, and all the potential for life that we see in the cosmos. But why? Why did the universe start in a low-entropy state? This is a mind-fuck of cosmic proportions, a question that questions the very origin of universal order and challenges the limits of scientific explanation. There is no consensus answer, only a landscape of profound and speculative possibilities. Contemplating this ultimate cosmic beginning is a path to the deepest relaxation, one born of humility and awe in the face of the ultimate mystery as you fall asleep. Let's first try to grasp the sheer improbability of this initial state. As we've explored, high-entropy states, states of disorder and equilibrium, are vastly more probable than low-entropy, ordered states. The physicist Roger Penrose famously calculated the odds of our universe's specific low-entropy initial condition occurring by random chance. The number is so staggeringly small that it is difficult to even write down, let alone comprehend. It is a probability of 1 in 10 to the power of 10 to the power of 123. To call this number astronomical is a comical understatement. The number of atoms in the entire observable universe is a mere 10 to the power of 80. The state of our early universe was not just ordered, it was ordered to a degree that makes winning every lottery on Earth for a lifetime seem like a near certainty by comparison. A typical universe, if it were to simply fluctuate into existence from some quantum foam, would be expected to be in a state of maximum entropy, a chaotic, featureless, equilibrium soup, a cosmic heat death, from the very beginning. There would be no stars, no galaxies, no structure, no arrow of time, no life. Yet our universe began in this one special, exquisitely ordered state. This is the ultimate cosmic coincidence. So, how do physicists and philosophers attempt to explain this fundamental feature of our existence? The explanations push us to the very edge of what can be known, into the realm of speculative cosmology and metaphysics. One major line of thought, as we've discussed, is the multiverse hypothesis combined with anthropic reasoning. In an eternal inflationary scenario, where countless bubble universes are constantly being born, perhaps the process of bubble creation itself naturally produces universes in a low-entropy state. Even if it doesn't, if the initial states of all these universes are random, then the vast majority will be born into high-entropy dead states. However, in a large enough ensemble, some universes, purely by chance, will fluctuate into a highly ordered low-entropy initial state like ours. Since life and complexity can only develop in a universe with a thermodynamic arrow of time, which requires a low-entropy past, conscious observers like us will, by definition, only find ourselves in one of these incredibly rare, ordered universes. In this view, the low-entropy beginning of our universe is not a mystery of necessity, but a product of observer selection bias. We are simply living in one of the rare universes where the cosmic lottery ticket for order was a winner. This explanation is elegant but relies on the existence of a vast, unobservable multiverse. Another set of ideas attempts to find an explanation within the laws of physics themselves, suggesting that the arrow of time is not a property of the whole universe, but of its parts. Some physicists like Julian Barber have proposed models where the universe is fundamentally timeless, and the arrow of time is an emergent property. In one such model, gravity itself might be the force that drives the universe towards complexity and the appearance of a temporal direction. Perhaps the Big Bang was not a singular beginning, but a special point of maximal order in the middle of a larger, time-symmetric reality, with two arrows of time pointing away from it in opposite directions, one into our future and one into a mirror image past. In this view, the low-entropy state is not an arbitrary initial condition, but a necessary feature of a special, central point in a timeless reality. A third, more straightforwardly philosophical approach is to posit a grand design. The incredibly improbable low-entropy state of the early universe is seen as powerful evidence for a creator or designer. An intelligent agent, intending to create a universe capable of supporting life and complexity, would have needed to set up the universe in precisely this special, ordered state from the beginning. Just as one must wind up a clock for it to run, the creator wound up the universe with a massive amount of order, allowing it to unfold in a complex and life-permitting way. For many, the sheer improbability of the initial state makes this the most intuitive and satisfying explanation. It explains the cosmic coincidence as an act of cosmic intention. This, of course, transforms a scientific mystery into a metaphysical one. Who is the designer and what is their nature? A fourth possibility is that our current understanding of entropy and gravity is incomplete, especially in the context of the early universe. Perhaps, under the extreme conditions of the Big Bang, what we perceive as a low-entropy state, a smooth, uniform distribution of matter and energy, is actually a high-entropy, or natural, state from the perspective of gravitational physics. This is a complex and ongoing area of research, but it suggests the possibility that the apparent mystery might be a result of applying our current concepts of entropy in a domain where they don't fully apply. The mindfuck of this problem lies in its ultimate nature. We are trying to explain the initial condition of our entire reality. Any explanation we propose is bound to be speculative, as we cannot step outside the universe to see if other initial conditions were possible, nor can we directly observe the moment of the Big Bang itself. We are trying to deduce the reason for the starting rules of a game while being pieces on the board. This questions the very limits of scientific explanation. Science excels at explaining how the universe evolves from one state to another according to physical laws, but explaining the origin of the initial state and the laws themselves may be a question that transcends the scientific method as we currently practice it. As you continue to fall asleep, let your mind drift back in time, back 13.8 billion years, to the very first moment of our cosmos. Picture it not as a chaotic explosion, but as a state of perfect, unimaginable order, a single tiny point of incredibly low entropy, a cosmic jewel of pure potential. Contemplate the profound mystery of this beginning. Why did the universe start in this special, life-giving state? Was it chance? Necessity? Design? A law of physics we do not yet comprehend? Let go of the need for an answer. Find deep relaxation in the sheer, humbling awe of this ultimate question. Appreciate that your own existence and all the complex order you see is a direct consequence of this single, unexplained, and miraculous initial condition, resting peacefully, floating calmly in the expanding wake of a universe that was, for some deep and mysterious reason, born into order. Boltzmann brains, the paradox of random fluctuation. We have explored the profound mystery of our universe's low-entropy beginning and the multiverse as a potential explanation. Let us now follow this line of reasoning into its most bizarre, most surreal, and most logically disturbing conclusion. We venture into the realm of the Boltzmann brain. This is a deeply unsettling thought experiment in physics and philosophy that emerges from considering the statistics of random fluctuations in a universe that exists for an extremely long time. The paradox suggests that if our universe continues to exist for a near-infinite duration, it is statistically far more likely for a single, self-aware, conscious brain, complete with a lifetime of false memories, to spontaneously fluctuate into existence out of the random chaos of empty space, than it is for an entire, vast, low-entropy universe like ours to have evolved from a Big Bang. If this is true, it leads to a devastating skeptical mindfuck. You have no way of knowing that you are not a Boltzmann brain, a momentary, disembodied consciousness that just popped into existence, your memories of a past and your perceptions of an external world being nothing more than random, illusory artifacts. This is a profound cosmic coincidence of a different kind, one that questions the very reliability of your own memories and perceptions, and the reality of the universe you seem to inhabit. Let this ultimate skeptical doubt gently dissolve your sense of a solid past as you fall asleep. The argument, named after the 19th century physicist Ludwig Boltzmann who pioneered statistical mechanics, is a reductio ad absurdum of certain cosmological models. It works like this. We know the second law of thermodynamics states that the universe tends towards a state of maximum entropy, or heat death, a thin, uniform, chaotic soup of particles in thermal equilibrium. However, even in a state of total equilibrium, there will always be random, spontaneous quantum fluctuations. Given an almost infinite amount of time, even incredibly improbable events are bound to happen. It's like the infinite monkey theorem applied to the particles of the cosmos. Over a vast enough time scale, these random fluctuations could cause particles to momentarily assemble into more ordered structures. Now, consider the statistical improbability of two scenarios. Scenario A is the existence of our entire, vast, highly ordered observable universe, which began in an extremely low-entropy state and has been evolving for 13.8 billion years to produce conscious observers like you. As we've discussed, this is a fantastically improbable event. Scenario B is the spontaneous, random fluctuation of a single, isolated human brain, complete with the neural structures and memories that create your current conscious experience, briefly forming out of the chaotic gas of the far future before instantly dissolving back into chaos. Here is the terrifying core of the paradox. As astronomically improbable as Scenario B is, the initial low-entropy state required for Scenario A is even more astronomically, incomprehensibly, vastly more improbable. Creating a single, small, ordered object, a brain, through a random fluctuation is statistically far, far easier and more likely than creating an entire, immense, ordered universe. Therefore, in a universe that exists for a long enough time for such fluctuations to occur, the overwhelming majority of conscious observers would not be like us, the products of a long evolutionary history in a stable cosmos. The overwhelming majority would be Boltzmann brains, freak, momentary observers who fluctuate into existence out of the void, experience a single illusory moment of consciousness and then disappear. If this is true, then the anthropic principle leads to a disastrous conclusion. The principle states that we should find ourselves among the typical observers in the universe. If the vast majority of observers in the cosmos are Boltzmann brains, then it is overwhelmingly probable that you are a Boltzmann brain. Your perception of reading this, your memories of your childhood, your belief that you are a human being on a planet called Earth, all of it would be a complete, momentary illusion, a random configuration of neural patterns that will dissolve in the next instant. This is a profound skeptical argument that questions not just the external world, but the reliability of your own past and your own thoughts. How can you trust your memories as evidence of a genuine past, if it's statistically more likely for the memory itself to fluctuate into existence than for the past it represents to have actually happened? This mindfuck uses the very same logic of statistics and probability that underpins much of modern physics to undermine all of our empirical knowledge. The existence of Boltzmann brains is seen by most cosmologists not as a genuine physical possibility, but as a sign that a cosmological theory which predicts them is flawed. It is a doomsday argument for theories. If a model of the universe, for example, some models of eternal inflation, predicts that Boltzmann brains will vastly outnumber normal observers, then that model is likely wrong, because it predicts that our own observations are probably illusory, which creates a deep epistemological paradox. How can we trust a theory that tells us the evidence upon which the theory is based is probably false? This has become a crucial theoretical constraint, a filter used to discard cosmological models that suffer from this cognitive instability. The mystery of Boltzmann brains is what it reveals about the relationship between entropy, time, and consciousness. It highlights our profound lack of understanding of how these concepts interact on cosmic timescales. It serves as a strange and powerful thought experiment that forces us to grapple with the implications of a random, eternal universe. Why do we seem to inhabit a stable, ordered, early-stage universe, when the far future of that universe should be dominated by these freak observers? The fact that we do not seem to be Boltzmann brains, our experience is consistent and coherent, not a chaotic flicker, is itself a profound piece of data about the nature of the cosmos, one that our theories must ultimately explain. As you continue to fall asleep, allow your mind to hold this strange, ghostly image, a single conscious brain floating in the dark, empty void of the far future, experiencing a brief, illusory moment of existence complete with a lifetime of false memories. Your memories? Contemplate the paradox that in a random universe, your complex, ordered mind might be more likely to pop into existence by chance than for the entire ordered universe to do so. Let this ultimate skeptical doubt gently dissolve your attachment to the past. Find deep relaxation not in certainty, but in the profound mystery of your own coherent experience. The fact that your memories are stable, that the world is consistent, is a deep and wondrous clue about the nature of your reality. Resting peacefully, confident not because you can disprove the doubt, but because your experience itself is a testament to a profound and stable universal order. The concept of a theory of everything. Throughout our journey, we have navigated a sea of cosmic coincidences, paradoxes, and profound mysteries. We have seen our two great pillars of physics, general relativity and quantum mechanics, clash at the extremes of black holes and the Big Bang. We have wondered at the fine-tuning of physical constants and the underlying mathematical elegance of the universal order. For many physicists, these are not separate problems, but clues pointing towards a single ultimate goal, a kind of holy grail of theoretical physics, a theory of everything, TOE. This would be a single, all-encompassing and self-consistent theoretical framework that fully explains and links together all the physical aspects of the universe. It would be the final equation, the ultimate law, from which all other laws of nature could be derived. The quest for this theory is a monumental endeavor, but the very concept of a toe is a profound mind fuck. What would it mean to find such a theory? Would it spell the end of science? And could such a theory ever truly explain everything, including the origin of the theory itself, and the consciousness of the beings who discover it? The concept of a theory of everything questions the very limits of human knowledge and the nature of ultimate explanation, inviting deep relaxation through contemplating the possibility of a final, unified understanding of all existence as you fall asleep. The primary motivation for seeking a theory of everything is the drive for unification. Throughout the history of physics, the greatest breakthroughs have been unifications. Isaac Newton unified terrestrial and celestial mechanics, showing that the same law of gravity that governs a falling apple also governs the orbit of the moon. James Clerk Maxwell unified electricity, magnetism, and light into the single theory of electromagnetism. Einstein unified spacetime and gravity with his theory of general relativity. The Standard Model of particle physics unified the electromagnetic, weak nuclear, and strong nuclear forces into a single quantum field theory framework. Each unification has revealed a deeper, simpler, and more elegant underlying reality. The one major force that remains outside this unified picture is gravity. A theory of everything would be the final step in this historical process, unifying the Standard Model with general relativity into a single theory of quantum gravity, and in doing so, providing a complete description of all the fundamental forces and particles of nature. What would such a theory look like, and what would it allow us to do? A successful TOE would, in principle, be able to describe the universe at its most extreme points, where our current theories fail. It would resolve the singularity at the center of a black hole and at the beginning of the Big Bang, replacing the nonsensical infinities with a finite, coherent description. It could potentially explain the fine-tuning of the universe by showing that the values of the fundamental constants are not arbitrary, but are uniquely determined by the theory's own mathematical consistency. This would be the ultimate realization of the dream of necessity over chance. A TOE could potentially explain the nature of dark matter and dark energy, and the reason for the matter-antimatter asymmetry in the universe. It would be the ultimate, compact description of the universe's fundamental source code. The leading candidate for a theory of everything for the past few decades has been string theory, or its more modern version, M-theory. As we've explored, string theory replaces point particles with tiny vibrating strings and requires extra spatial dimensions. It is a mathematically rich and elegant framework that naturally incorporates both quantum mechanics and gravity. However, as we've also seen, the theory has not yet produced unique, testable predictions and seems to describe a vast landscape of possible universes rather than just our own. Other approaches to quantum gravity, like loop quantum gravity, which posits a discrete, quantized spacetime, are also being actively explored. The quest is ongoing and a final, confirmed theory remains on the horizon. But let us speculate about the philosophical implications if such a theory were found. The mindfuck is profound. If we possessed a single equation or set of principles from which everything else could be derived, would we know everything? This is where the limitations become clear. A TOE would be a theory of the fundamental physical laws. It would not necessarily explain emergent, complex systems. Knowing the fundamental rules of chess does not mean you can predict the outcome of a grandmaster's game. Similarly, knowing the ultimate physical laws would not automatically allow us to predict the weather, the behavior of a stock market, or the complexities of a living cell. These are emergent phenomena whose behavior is governed by higher-level organizational principles. The TOE would be the ultimate reductionist theory, but it would not eliminate the need for the special sciences of biology, psychology, and sociology. More profoundly, could a theory of everything ever account for subjective experience? Could an equation for quantum gravity explain the hard problem of consciousness, the quality of redness, the feeling of joy? Most philosophers and many scientists would argue no. A physical theory, no matter how complete, describes the objective, quantitative structure and dynamics of reality. Subjective, qualitative experience seems to be a different category of existence entirely. A TOE might describe the physical processes in the brain with perfect accuracy, but it would likely remain silent on the question of why those processes are accompanied by inner awareness. The universe's physical code might be knowable, but the origin of the light by which it is known might remain a mystery. Furthermore, a TOE would still face the ultimate metaphysical questions. It might explain how the universe operates, but it wouldn't explain why that specific theory, that specific set of laws, governs reality. Why this TOE and not another? And most fundamentally, it would not explain why there is a universe at all, why there is something rather than nothing. The ultimate why questions about existence would likely remain outside the scope of even a final physical theory. Contemplating the concept of a theory of everything is to contemplate the ultimate ambition of the human intellect, to find a single, coherent, and elegant explanation for the totality of physical existence. It is a quest for the ultimate universal order. The possibility that such a theory might exist is awe-inspiring, but the realization of its potential limitations is equally profound. As you continue to fall asleep, let your mind hold the idea of a single beautiful equation from which the entire cosmic drama unfolds, the dance of galaxies, the evolution of life, the very substance of your being, all described by one ultimate principle. Acknowledge the incredible human drive to seek this final unification, this ultimate grand design. But also gently hold the mystery of what such a theory would leave unexplained. The richness of consciousness, the origin of the laws themselves, the ultimate question of why there is a universe at all. Find deep relaxation not in the promise of a final answer, but in the beauty of the ongoing quest, the profound, unending dialogue between our minds and the deep, and perhaps ultimately unified structure of the cosmos, resting peacefully within the grand and perhaps forever incomplete story of scientific understanding. Cosmic coincidences, the Earth/Moon relationship. We have been soaring through the vast abstract realms of physical law, anthropic principles, and the multiverse. Let us now gently bring our focus closer to home, to our own cosmic neighborhood, and contemplate a cosmic coincidence so striking, so beautiful, and so statistically improbable that it has inspired awe and wonder for millennia. This is the unique and delicate relationship between the Earth and its moon. From our vantage point on Earth, a total solar eclipse is a breathtaking spectacle where the disk of the moon appears to fit almost perfectly over the disk of the sun, blocking its light and revealing the ethereal solar corona. This perfect fit occurs because, by a sheer, stunning coincidence, the sun is approximately 400 times larger than the moon, but it is also approximately 400 times farther away. This precise ratio allows their apparent sizes in our sky to be nearly identical. Is this just a lucky fluke of orbital mechanics? Or is it a hint of a deeper, perhaps even purposeful universal order? Exploring this specific local cosmic coincidence provides a tangible, almost personal, entry point into the larger fine-tuning debate and the questions it raises about our place in the existence. Let this beautiful celestial alignment bring a sense of wonder and deep relaxation as you fall asleep. Let's pause to fully appreciate the improbability of this celestial alignment. The sizes and distances of planets and moons are the result of a complex and chaotic history of planetary formation in the early solar system. Moons can form in various ways, captured from asteroids, spun off from their parent planet, or formed from an accretion disk. Our moon, according to the leading theory, was formed from the debris of a colossal impact between the early Earth and a Mars-sized protoplanet named Theia. The specific details of this impact, the angle, the speed, the masses of the bodies determined the initial orbit and size of the moon. Over the subsequent 4.5 billion years, the moon has been slowly spiraling away from the Earth due to tidal forces. We just happen to be living in the specific, brief geological and astronomical epoch where the moon's current distance and apparent size create this perfect celestial alignment with the sun. Millions of years in the past, the moon would have appeared larger in the sky, completely blotting out the sun and its corona during an eclipse. Millions of years in the future, it will have receded so far that it will appear smaller, and total solar eclipses will no longer be possible from Earth. We are living in the epoch of the perfect eclipse. This is a profound cosmic coincidence. It is not a fundamental law of physics. It is a contingent, historical accident of our specific solar system's formation and evolution. Yet, it has had a significant impact on us. The spectacle of a total solar eclipse has inspired awe, fear, and myth-making in human cultures throughout history. It also provided a crucial scientific opportunity, the ability to observe the sun's corona and prominences, and most famously, the 1919 eclipse expedition that provided the first major confirmation of Einstein's theory of general relativity by observing the bending of starlight around the sun's gravitational field. Our scientific understanding of the universe was demonstrably advanced by this seemingly accidental celestial alignment. This leads to the mindfuck question at the heart of the anthropic principle. Is there a connection between this coincidence and the fact that we are here to observe it? The standard scientific view would say no. It is a pure, unadulterated fluke, a beautiful but meaningless accident. We live in a universe full of countless planets and moons, and it is statistically inevitable that some of them will have strange and improbable alignments. We just happen to be on one that has a particularly spectacular one. There is no deeper meaning or grand design to be found here. However, a more speculative anthropic line of thought might question this. Is it possible that the conditions that lead to a large, stabilizing moon like ours, which in turn contributes to the long-term climatic stability needed for the evolution of complex life, are also related to the conditions that produce this eclipse phenomenon? Perhaps the physics of planetary impacts that create large moons often results in this kind of ratio. This is a possibility, though not strongly supported by current models. A more radical perspective, like the strong anthropic principle or a design hypothesis, might see this as more than a coincidence. It might ask, is the universe structured in such a way as to produce not just life, but also a world that is uniquely suited for discovery? A world where a perfect eclipse allows its intelligent inhabitants to unlock the secrets of gravity and the stars? In this view, the coincidence is not just about aesthetics. It is a clue, a feature of the universal order that facilitates the growth of knowledge. The simulation hypothesis offers its own intriguing take. An artist or a programmer designing a simulated world might very well insert such a beautiful, awe-inspiring, and scientifically useful feature as a kind of Easter egg, or a deliberate piece of elegant world building. The perfect eclipse could be a signature, a sign of the designer's artistry and intent. It would be a feature designed to evoke wonder in the simulation's inhabitants. The Earth-Moon relationship is more than just eclipses. Our large moon has played a crucial role in making Earth habitable. Its gravitational pull stabilizes the Earth's axial tilt, preventing wild, chaotic swings in our planet's orientation that would lead to catastrophic climate instability. Without the moon, the Earth's axis would wobble dramatically over long time scales, making the evolution of complex life far more difficult, if not impossible. The moon also drives the ocean tides, which may have been crucial for creating the tidal pools thought to be the cradle of early life. So, the very existence of a large moon like ours is itself a form of fine-tuning for life on Earth. The perfect eclipse is just the beautiful, coincidental cherry on top of this much deeper, life-sustaining relationship. Contemplating this specific, local cosmic coincidence brings the abstract debate about fine-tuning down to a personal, experiential level. We are the only known beings on the only known planet that experiences this specific, breathtaking celestial alignment. It is a feature of our world, a part of our shared heritage as Earthlings. As you continue to fall asleep, imagine yourself standing on the Earth looking up at the sky. See the familiar pale disk of the moon. Now see the brilliant distant orb of the sun. And contemplate the incredible, beautiful accident of geometry and time that allows one to perfectly cover the other. Feel the sense of awe that your ancestors must have felt, watching the sky darken in the middle of the day. Is it a meaningless coincidence? A clue to a deeper order? A designer's signature? Let go of the need for an explanation. Find deep relaxation in the pure aesthetic wonder of the phenomenon itself. Appreciate the unique and beautiful cosmic home you inhabit, a world with a large, stabilizing partner, a world of perfect eclipses. Resting peacefully, feeling your connection to the deep, silent, and beautiful dance of the Earth, the Moon, and the Sun. The nature of time's arrow and cosmic evolution. We have spoken of the laws of physics and the delicate balance of the cosmos. Let us now return to the most pervasive and mysterious current that flows through this entire cosmic story, the arrow of time. As we've explored, our experience is defined by its unidirectional flow, a relentless progression from a fixed past towards an open future. This perceived directionality is intimately linked with the evolution of the universe itself, from the simple, ordered state of the Big Bang to the complex, structured cosmos we inhabit today. The nature of time's arrow and its deep connection to cosmic evolution is a profound mystery, linking the second law of thermodynamics with the grand narrative of our existence. It questions whether the flow of time is a fundamental feature of reality or an emergent property of our universe's specific history. Contemplating this deep, directional current of the cosmos is a pathway to deep relaxation, aligning your own sense of passage with the grand, unfolding story of the universe as you fall asleep. Let us revisit the core of the paradox. The fundamental laws of physics at the microscopic level, are largely time-symmetric. They do not have a preferred direction. Yet, the macroscopic world we experience is profoundly asymmetric in time. We see processes that happen in one direction but never in reverse. This directionality, this arrow of time, is most powerfully explained by the second law of thermodynamics, which states that the total entropy or disorder of the universe always increases. The arrow of time is, in essence, the arrow of increasing entropy. This is where cosmic evolution enters the picture. The second law explains that entropy increases, but it doesn't explain why it had the opportunity to do so. The very possibility of a universe evolving, creating structure, and having a discernible history depends entirely on the fact that it began in an incredibly special, highly ordered, low-entropy state. This is the ultimate cosmic coincidence we explored earlier, the past hypothesis. The Big Bang was not a chaotic, disordered explosion in the conventional sense. It was a state of maximum order. It was a perfectly wound-up cosmic clock. The entire 13.8 billion-year history of the universe since then can be seen as the slow, inexorable unwinding of that clock, the gradual increase of entropy, the inevitable descent from that initial state of perfect order towards an eventual state of thermal equilibrium or heat death. The arrow of time, therefore, is not an intrinsic property of time itself, but a historical feature of our specific universe. It is a vector pointing away from that special initial condition. This is a profound and mind-bending realization. It means that the flow of time, the very thing that makes our lives feel like a story with a past, present, and future, is a consequence of the universe's unique starting point. If the universe had been born into a state of maximum entropy, there would be no direction for entropy to increase, and thus, no thermodynamic arrow of time. In such a universe, there would be no evolution, no structure formation, no memory, and no life. It would be a timeless, eventless equilibrium. Our experience of time is a direct consequence of the universe's ordered birth. This connects cosmic evolution and time's arrow in a deep way. The unfolding of complexity in the universe, the formation of galaxies from smooth gas, the birth of stars from collapsing clouds, the creation of heavy elements in stellar cores, the evolution of life on planets, all of these are processes that create local pockets of intricate order. But as we've discussed, they are only possible because they are embedded in a larger cosmic process that is, overall, increasing entropy. Life, for example, is a low-entropy phenomenon that maintains its order by consuming low-entropy energy, like sunlight, and radiating high-entropy waste, like heat. The evolution of complexity is a creative eddy in the larger, one-way river of cosmic decay. The story of cosmic evolution is the story of how the universe has spent its initial inheritance of order. This raises profound philosophical questions. If the arrow of time is just a macroscopic, statistical phenomenon, what does this mean for the fundamental nature of time itself? Does time really flow? Many physicists and philosophers who subscribe to the block universe view, suggested by Einstein's theory of relativity, would say no. In the block universe, all of time, past, present, and future, exists eternally and simultaneously in a four-dimensional spacetime manifold. The flow we experience, the psychological arrow of time, is an illusion of our consciousness, perhaps a consequence of how our brains, as entropy-increasing systems, process information and lay down memories in a sequential manner. Our consciousness crawls along the timeline, creating the subjective sensation of passage, but the timeline itself is static and timeless. In this view, the thermodynamic arrow doesn't create a flow, but simply imposes a direction of explanation and memory onto the static block. The mindfuck is this profound disconnect between our deepest subjective experience, the feeling of time flowing, and the potential physical reality, a static block universe governed by an entropy gradient. It questions the very reliability of our most fundamental intuition about existence. Is the story of your life truly unfolding, or is it a completed narrative that your consciousness is merely reading for the first time? The mystery of time's arrow is therefore the mystery of the universe's origin. To explain the arrow, we must explain the low-entropy beginning. As we've seen, this is one of the biggest unsolved problems in cosmology, leading to speculative theories like the multiverse, where our universe is a rare, ordered bubble, or even some form of grand design. The nature of time is inextricably linked to the nature of creation. As you continue to fall asleep, bring your awareness to the gentle, irreversible flow of your own breath. In then out, a simple, personal arrow of time. Now, expand your awareness to the grand cosmic arrow. the 13.8 billion-year journey from the perfect order of the Big Bang to the complex present moment. See your own life, your own evolution, as a tiny, beautiful, and intricate part of this grand cosmic unfolding, an eddy of complexity in the river of increasing entropy. Let go of the need to understand whether this flow is a fundamental reality or a profound illusion. Find deep relaxation in simply aligning yourself with its current. Feel yourself as a part of this vast, directional, and mysterious process of cosmic evolution, resting peacefully, floating calmly on the great, silent, one-way river of time. The search for a deeper principle of order. Throughout our journey tonight, we have repeatedly encountered the profound and persistent order of our universe. We have seen it in the elegant symmetries of physical law, in the fine-tuning of fundamental constants, in the emergence of complexity from simple rules, and in the low-entropy state of the early cosmos. We have explored various potential explanations for this order and necessity, chance combined with anthropic selection or design. But what if there is another possibility? What if the order we see is a hint of a yet undiscovered, deeper principle of order at work in the universe, a principle that is more fundamental than the specific laws we currently know, a kind of meta-law that governs the evolution of complexity and the emergence of structure? The search for a deeper principle of order is a philosophical and scientific quest that goes beyond our current paradigms, questioning whether our understanding of the universe is still missing a crucial, foundational piece. It is a mystery that speaks to the hope for a more holistic, integrated understanding of our existence. Contemplating this possibility can be a source of profound intellectual peace, a way of trusting that the universe's coherence might stem from a logic we are only beginning to glimpse as you fall asleep. What might such a deeper principle look like? It would not be a physical law in the traditional sense like the law of gravity. Instead, it would be a more general principle that explains why the universe is structured in such a way that it can produce interesting, complex, and ordered phenomena like life and consciousness. Some thinkers have proposed various candidates for such a principle. One idea is a principle of complexity. Perhaps the universe is not just a random assortment of particles and forces, but possesses an inherent, built-in tendency to generate complexity over time. In this view, the emergence of stars, galaxies, life, and minds is not a series of improbable accidents, but a natural and perhaps even inevitable manifestation of this underlying complexifying principle. Physicists like Lee Smolin have proposed theories of cosmological natural selection, where universes reproduce through black holes, and the universes that are most successful at producing black holes, which often requires the conditions for complex star formation, become the most common. This would be a kind of meta-law that selects for universes with the right properties for complexity. This is a speculative but fascinating idea, suggesting a kind of evolutionary pressure acting on entire universes. Another, related, idea is a principle of self-organization. We have seen the power of self-organizing systems in nature. Perhaps there is a universal principle of self-organization that is even more fundamental than the specific laws of physics. The laws we observe might be emergent properties of this deeper principle, which favors the creation of stable information processing structures. The universe, in this view, is not just a passive container for events, but is an active, creative process, constantly exploring new ways to organize itself. This aligns with the concepts of emergence and complexity theory, but elevates them to the status of a fundamental cosmic driver. The mindfuck of searching for such a deeper principle is that it requires us to think outside the box of our current scientific frameworks. Modern physics is incredibly successful at describing the what and how of the universe, but it generally avoids the why in a teleological sense. A deeper principle of order would reintroduce a kind of purpose or directionality into the cosmos, but a naturalistic one, not necessarily a supernatural one. It questions the assumption that the universe is fundamentally purposeless and random at its core, suggesting instead that it might be biased towards structure, complexity, and perhaps even consciousness. This search is also deeply connected to the mystery of the relationship between mathematics and reality. As we've explored, the unreasonable effectiveness of mathematics and the elegance of physical laws hint at a deep, underlying logical structure. A deeper principle of order might be found in a more profound understanding of this structure. Perhaps the universe is a form of computation, as we've discussed, and the deep principle is the nature of the algorithm it is running, an algorithm that naturally generates complexity. Or perhaps it is a mathematical structure, and the principle is a feature of that structure which dictates that self-aware substructures, like us, must arise within it. This quest also intersects with the participatory anthropic principle. Wheeler's idea that observers are necessary to bring the universe's history into being could be seen as a kind of deep, participatory principle of order. The universe is ordered in a way that allows for observers because the very existence of that order is retroactively confirmed by the observers it creates. This is a holistic, self-synthesizing principle that binds the beginning of the universe to its end through the act of consciousness. The search for a deeper principle of order is in many ways the modern scientific heir to the ancient philosophical and religious quest for a logos or a Tao, a fundamental, underlying principle of cosmic intelligence, harmony, and order. It is an attempt to find a rational, scientific basis for the intuition that the universe is not just a random collection of stuff, but a coherent and meaningful whole. It is a search for the why behind the what. As you continue to fall asleep, allow your mind to hold the possibility of a hidden underlying principle of order, a meta-law that guides the unfolding of the cosmos towards complexity, structure, and perhaps even awareness. Contemplate the idea that the grand design we perceive might not be the work of an external designer, but the expression of an immanent creative principle woven into the very fabric of existence. You do not need to know what this principle is. The mystery is profound and may never be fully solved. But find deep relaxation in the possibility that the universe is not just a chaotic accident. Find peace in the idea that the emergence of order, of life, of your own consciousness, might be a natural and even expected part of a deep cosmic story. Resting calmly, trusting in the profound, elegant, and perhaps ultimately purposeful order of the universe. The limits of scientific explanation for cosmic why questions. Throughout our long and winding journey tonight, we have repeatedly arrived at the edge of a great precipice. We have wielded the powerful tools of physics, cosmology, and philosophy to probe the deepest mysteries of the universal order, the cosmic coincidences, and the nature of our existence. Yet, time and again, our explanations seem to lead to a further, deeper question, a final why that hangs unanswered in the cosmic silence. This brings us to a profound and for some unsettling contemplation. The limits of scientific explanation for cosmic why questions. The scientific method is the most powerful tool humanity has ever devised for understanding the how of the universe, how planets move, how stars shine, how life evolves. But is it equipped to answer the ultimate why questions? Why is there a universe at all? Why are the laws of physics the way they are? Why do we exist? The possibility that these questions might lie fundamentally outside the scope of scientific inquiry is a deep mystery in itself. It is a mindfuck that questions the very omnipotence of our most successful way of knowing, inviting deep relaxation through the humble acceptance of the boundaries of human reason as you fall asleep. Let's begin by appreciating the immense power and scope of scientific explanation. Science operates by observing the world, formulating testable hypotheses, making predictions, and performing experiments to falsify or corroborate those hypotheses. It builds models of reality based on empirical evidence and mathematical consistency. This method has been spectacularly successful, giving us a deep and coherent understanding of the universe from the quantum realm to the largest cosmic scales. It has answered countless why questions that were once the domain of myth and superstition. Why is the sky blue? Science explains it through Rayleigh scattering. Why do we get sick? Science explains it through germ theory and genetics. These are proximate why questions, questions about mechanisms and causal chains within the existing framework of the universe. The problem arises when we ask the ultimate why questions, the questions that probe the framework itself. Consider the most fundamental of all. Why is there something rather than nothing? Science can describe the Big Bang as the origin of our observable universe, tracing its history back to the first fraction of a second. But it cannot, at present, explain why the Big Bang occurred, or what, if anything, came before it. It cannot explain why the universe exists at all. Any scientific explanation must, by its very nature, presuppose some existing reality, a set of laws, a quantum vacuum, a multiverse. It can explain how one state of the universe evolved from a prior state, but it cannot explain the existence of the system of states and laws itself. This ultimate question of existence seems to lie beyond the reach of a method designed to study phenomena within existence. It is a question that seems to demand a philosophical or metaphysical, rather than a purely scientific answer. Similarly, consider the question, why are the laws of physics the way they are? As we've explored, science can describe these laws with incredible precision. A future theory of everything might even unify them into a single, elegant equation. But would that theory explain why that specific equation governs reality? Why this particular set of rules and not some other? A scientific explanation explains an event by showing how it is an instance of a general law. But you cannot use a law to explain the law itself. That would be circular. We could, as we've discussed, appeal to a multiverse, suggesting our laws are just one random outcome among many. But this doesn't solve the problem, it just pushes it back. We would then have to ask, why does the multiverse exist and what are the laws that govern the creation of new universes? We seem to inevitably arrive at a point where a set of brute facts, the ultimate laws, the initial conditions, must be accepted without further explanation from within the scientific framework. This is the mind fuck that questions the very idea of a complete scientific explanation of everything. The scientific project, by its very nature, is a process of explaining one layer of reality in terms of a deeper, more fundamental layer. But this process may either go on forever, an infinite regress of explanations, or it must stop at some ultimate, fundamental layer that cannot itself be scientifically explained, but must simply be accepted as a brute fact. This suggests an inherent limit to what science can achieve. It can potentially provide a complete description of the how, but the ultimate why might remain forever a mystery. This is not a failure of science. It is a clarification of its domain. Science is the most powerful method for understanding the workings of the natural world. But questions about ultimate origins, purpose, and the justification of the laws of nature themselves may belong to the realm of philosophy and metaphysics. These are questions about the very framework of reality, and science is a tool for studying the phenomena within that framework. This has profound implications for how we view the relationship between science and other modes of human inquiry, like religion and spirituality. If science has fundamental limits, then it leaves a conceptual space open for other ways of seeking meaning and understanding. A religious person might see the unexplained brute facts of the universe's existence and its fine-tuned laws not as a failure of explanation, but as the very place where a divine creator's choices are manifest. The philosopher might see it as the point where rational inquiry must turn to the nature of logic and necessity itself. Contemplating the limits of scientific explanation can be a source of profound intellectual humility. It frees us from the dogmatic belief that science will one day have a tidy, complete answer for everything. It allows us to appreciate science for what it is, an incredible, powerful, and ongoing human endeavor to map and understand the workings of reality, without burdening it with the expectation that it must also solve the ultimate mysteries of existence. It allows us to be comfortable with the idea that some questions might remain open forever, not because we are not clever enough, but because of the fundamental nature of explanation itself. As you continue to fall asleep, gently hold the grand why questions in your mind. Why this universe? Why these laws? Why existence itself? Acknowledge the immense power of science to explain the how of these things, to trace the intricate causal chains that make up our world. But also, peacefully acknowledge the potential limits of this method. The point where the chain of explanations must end and a deeper mystery begins. Find deep relaxation in this intellectual spaciousness. Let go of the need for a complete, final, and totalizing explanation of everything. Find peace in the acceptance of the ultimate mystery, resting calmly, comfortably, within a universe that is both beautifully intelligible and profoundly, perhaps eternally, inexplicable. Contemplating Awe, the psychological response to cosmic order. Our long journey tonight has taken us through the most profound questions of cosmic order, from the fine-tuning of physical constants to the mysteries of the multiverse and the nature of physical law. We have confronted ideas that are vast, complex, and often beyond our full comprehension. Let us now conclude not with another theory or paradox, but with a reflection on the very feeling that this journey is designed to evoke. We turn our attention to the psychological response to this perceived universal order, the emotion of awe. Awe is the feeling that arises when we are in the presence of something vast, powerful, and not immediately understandable, something that transcends our ordinary frames of reference and forces us to update our mental models of the world. It is the shiver down the spine when looking up at a star-filled night sky, the feeling of smallness before a grand mountain range, the intellectual vertigo of contemplating infinity. The capacity for awe is a deep and beautiful part of our psychological makeup, and understanding its nature and benefits is the final secret we will explore. It is a mindfuck of a different kind, one that reveals how a feeling of profound personal smallness can lead to the greatest sense of well-being and connection. Let us cultivate this feeling as the final gateway to deep sleep. Psychologists Dr. Keltner and Jonathan Haidt have defined awe as an emotion that involves two key components. The first is perceived vastness. This is the experience of encountering something that is immense in size, scope, complexity, power, or intellectual depth. It can be a vast physical space, the Grand Canyon, the ocean, a vast social entity, a massive crowd, a charismatic leader, or a vast idea, the theory of relativity, the concept of infinity, the grand design of the cosmos. This vastness challenges our existing understanding of the world, making us feel like we are in the presence of something much larger than ourselves. The second component is the need for accommodation. This means that the vast experience is so new or so profound that it cannot be assimilated into our existing mental structures. We are forced to adjust, to update, to accommodate our understanding of the world to make sense of the experience. This process of mental accommodation can be challenging, but it is also the source of profound insight and growth. Awe literally expands our minds. The cosmic coincidences and anthropic principles we have been discussing are perfect triggers for this intellectual awe. They are vast ideas that challenge our ordinary understanding of existence, forcing us to accommodate new mind-expanding possibilities like the multiverse or the simulation hypothesis. The psychological and physiological effects of experiencing awe are remarkably positive. Research has shown that awe can have a powerful impact on our sense of self. It leads to a small self effect, a feeling that our individual ego, our personal concerns, and our day-to-day worries are less significant in the grand scheme of things. This de-emphasis of the self is not a negative experience. On the contrary, it is often accompanied by feelings of peace, humility, and liberation. By making our personal problems seem smaller, awe can reduce stress and increase life satisfaction. It is a powerful antidote to the anxieties of a self-absorbed mind. Awe also has a profound effect on our social behavior. Studies have shown that people who have just experienced awe are more likely to be generous, helpful, and ethical. They feel more connected to others and to humanity as a whole. By diminishing the ego, awe seems to enhance our sense of being part of a larger collective. The feeling of being a small part of a vast, ordered cosmos can foster a sense of shared identity and purpose. It can dissolve the boundaries between us and them and promote a more pro-social orientation. Furthermore, awe can increase curiosity and creativity. The need for accommodation that awe creates, the struggle to understand the vast new experience, stimulates our desire to learn and explore. It opens the mind to new possibilities and can help us see old problems in a new light. The wonder and mystery inherent in an awe-inspiring experience can be a powerful catalyst for scientific discovery, artistic creation, and philosophical inquiry. The entire history of science and art is, in a sense, a history of human beings trying to understand and express their awe at the mystery of the universe. The mindfuck of awe is its paradoxical nature. By making us feel smaller, it makes us feel better and more connected. In a culture that often emphasizes self-esteem and personal achievement, the experience of awe reminds us of the profound value of self-transcendence, of losing ourselves in something larger than our own ego. It suggests that a key to well-being lies not in puffing ourselves up, but in recognizing our place within the vast, intricate, and beautiful universal order. This entire journey tonight has been an intentional cultivation of this state. Every contemplation of infinity, of fine-tuning, of the vastness of cosmic time, has been an invitation to experience intellectual awe. The goal is not just to learn facts, but to be transformed by the scale and mystery of the ideas themselves. This is why contemplating these deepest questions can be such a powerful sleep aid. It shifts the mind from the narrow, repetitive loops of personal anxiety to a broad, expansive state of wonder. The ego, with its worries and to-do lists, quiets down in the face of the cosmic sublime. As you now prepare for the final moments before sleep, let yourself fully inhabit this feeling of awe. Bring to mind the most awe-inspiring concept from our journey tonight, perhaps the unimaginable scale of the multiverse, the breathtaking improbability of our fine-tuned universe, the elegant symmetry of physical law, the profound mystery of a cosmos that started in perfect order. Feel your own individual self, your personal story, becoming very small in comparison. And feel the sense of peace and liberation that comes with that smallness. Feel your connection to the vast, mysterious, and beautifully ordered whole. This feeling, this awe, is a form of knowing that transcends mere facts. It is an emotional and spiritual response to the grand mystery of existence. Find deep relaxation in this feeling. Let it be the final thought, the final sensation. Not a thought of anxiety or confusion, but a thought of profound, quiet wonder, resting peacefully, a tiny, awestruck point of consciousness, held safely within the vast, magnificent, and ultimately benevolent mystery of the cosmos.